Okay, time to get started. So this is a viewer requested stream on information theory. So hi Virus. Thank you very much for joining the stream. So today we're going to take a first look at information theory, and I'll be completely honest. This is also a new field to me. I never took a formal course. Hi, I'm good, thank you. I never take a formal course on information theory before, but I have been long interested in it. And so today, we will look at some of the most fundamental ideas, and we'll and just for me, I'll have a specific goal to accomplish. Let's see if I can manage to do that. I will explain that a bit shortly. So first things first, as you can see in this diagram, information theory is a highly interdisciplinary field. It's a product of the 20th century, and it has connections to so many different fields. Okay, for example, the fundamental notion in information theory called entropy comes from physics, and in particular, thermodynamics and statistical mechanics. And it also has to do with communication theory. Actually, this is where modern information theory became widely known. So it started as analysis of communication channels. So you have input and output, and we wish to minimize transmission errors, so to say. Okay, that's my very limited understanding. Okay, the prerequisite for this course is probability theory. Okay, just the regular probability. I will take a look at that. Okay, I'll talk about that in a second. So far, we're just gonna give some motivation for the subject. Okay, and probability theory, and in particular, we know that in probability we're interested in asymptotics, namely things like central limit theorem, law of large numbers, and it turns out that those things have an information theoretic perspective, okay, which as I'll be honest, I'm very ignorant about, and actually that's one of the main reasons I am interested in information theory, because I came from a probability and statistics background. And also, of course, statistics. Actually, today, one of the principal goals today is to understand the notion of sufficient statistics from an information theoretic standpoint. Okay, so if you've been following streams on this channel, we discuss the notion of sufficiency and minimal sufficiency in great details, if I may do say so that myself, in the past few streams. Okay, we characterized sufficiency from several equivalent standpoints, but those are all from the standpoint of statistical inference. But it turns out that you can formulate the notion of sufficient statistics in from an information theoretic standpoint as well, which is pretty cool. So there's that. And of course, it's a branch of mathematics. Then this is self-explanatory. And apparently it has to do with economics, such as portfolio theory and gambling strategy. Okay, I don't know too much about that. But I'll give you the main reference which we follow for this stream, which is in the title. Okay, anyway, in computer science, information theory is related to the concept of Kolmogorov complexity. Okay, so these are the main areas of applications as well as inspiration for information theory. Okay, and the book that we will follow is this one. So if we go to MIT OpenCourseWare, I'm not following a particular set of notes from MIT OpenCourseWare, unfortunately, but these are still great resources, in particular when it comes to their problem set. So I briefly take a look at information theory, the first entry as well as the second entry. Okay, so these two courses taught by different professors, but not the third one. The third one feels a little bit less mathematical. Okay, I think most people on this channel are interested in more mathematical content, and quite frankly, I am perhaps not very qualified when it comes to the engineering aspect of information theory. Okay, so let's stick to the first two options. So the first option, the top search result, if you type information theory, in MIT OpenCourseWare website. And those are the two search results. The first one taught by Professor Yuri Polyansky has full lecture notes. So as you can see, it has full lecture notes here. This is a great set of lecture notes. For example, if you go here and maybe I can zoom in a little bit. Yeah. If we zoom in a little bit, and you will see, come on, resolution. Damn, what's the resolution here? Anyway, so I'm saying is this particular note, we're not going to go through this notes today because it requires measure theory. Okay, so it requires measure theory, so it widely restrict the so to say, restrict the people who can follow this. Okay, so this is because in MIT OpenCourseWare, the prerequisite for this course is graduate level probability. However, even though I'm not an expert, I'm pretty certain to say that information theory does not require, the main intuition of information theory does not require measure theory. Okay, measure theory is just a convenient setup for proving various results in its full generality. However, to apply and understand the theory, measure theory is totally optional. Okay, so this is, I guess, that's what I can tell from the main text. Okay, that's the main text which we were following, elements of information theory. And based on my observation, if you have a basic course on not information theory, but probability theory, if you know how to calculate mean and variances, that sort of thing, then you can follow this text. Okay, all it takes is just some patience and time commitment. What's great about this website is it has extensive problem sets in addition to the existing problem sets in the textbook. Okay, and by the way, this textbook is, well, because it's copyright, I cannot share it on screen. I cannot put it on to show it on live. But if you search the title, Elements of Information Theory by T. Cover and J. Thomas, it will appear in a Google search result. Okay, so go ahead and enjoy while you still can, right? And that's the main source of information we are getting from. This is considered the Bible in information theory. It is very comprehensive and is widely used. So I think the citation is over like 10,000 or something. So it's very authoritative text. And as far as I can tell, it is also quite approachable. So the lecture notes, when it comes to mathematical sophistication, is at a higher level compared to the main text. Okay, but I think the problem sets can be done without dwelling on the measure theoretic detail. So don't be afraid to try it out, to try out some of the problems in this course package. All right, so that's the first option. And the second option also has lecture notes. However, these are more like slides. Okay, I don't know about you guys. I tend to prefer full lecture notes rather than slides. But slides, they do have their appeals. Okay, if you just wish to quickly go over some of the main ideas, slides are a great option. However, due to the format, it is sometimes not always easy to display all the subtleties in the theory. Okay, so there's that. And as far as I can tell, the second option does not use measure theory. Okay, so this particular setup. Okay, so here this is taught by Professor Muriel Medard. Okay, I don't know how to pronounce his name or her name, but that's the second option. And yeah, it also has a problem set. And many of the problems are taken straight from the textbook. So needless to say, two courses both heavily centered around the book that we're going to cover. So I don't know. At this point, I can make this a full series. I don't know, okay? Because right now my goals is rather limited. My goal is to simply understand the notion of sufficient statistics, okay? So here, if I just show the list of content, all right, So if I just show the list of content of the second chapter, the first chapter is like a preview, like an overview of the motivations as well as areas of applications for information theory. Because right now, because I always believe you can always talk loosely if you actually understand the details. Right now I don't, so I'm not going to talk about things that I don't yet understand. Instead, we're going to start from the fundamentals and just follow the definitions, the proofs, the problems, and whatnot. Okay, so here, this is my rather limited goal for today. Intended goal. I'm not sure this will actually be accomplished, but we try our best, right? This is what we always do. So that's what's going on here. Yeah, so that's the intended topics for today. But the idea is I'm going to set my goal to understand sufficient statistics, as I mentioned. Because actually, great shout out to Leo Lectures, another fellow YouTuber. So I think it was during last live stream, on my live stream for mathematical statistics, we were discussing sufficiency, and Leo brought up the perspective from information theory, which I completely did not follow at all. It was only later that I realized, oh, there's a completely new perspective on sufficient statistic. Okay, so, and there was a live stream, upcoming live stream, so I figured, why don't we just take that opportunity and try to understand sufficient statistic from an information theoretic point of view. But to do that, we need to start from the beginning, okay? And because I cannot show the text, it's going to be mostly me writing the stuff, which is a good practice. Okay, it's a good practice and a great way to absorb information. So without further ado, let's get into section 2.1, entropy. Okay, so hopefully, is there any more questions, such as if some Virat asked about the prerequisite? And I don't think there's much. Okay, you just need to know basic probability. That's enough. Okay, and if you really, really need measure theoretic probability, we can introduce that as we go along. Okay. Okay. 2.1, entropy. Okay, what is entropy? Okay, I apologize in advance if the definitions seem particularly motivated, because right now I cannot provide a good motivation simply because of the limited understanding I have on the subject. But however, I will try to be as accurate as possible. All right, so we first introduce the concept of entropy. What is entropy? Entropy is a measure of uncertainty. Measure of uncertainty in a random variable. Which kind of raises a question, right? We already have a measure of uncertainty in classic probability theory called a variance, right? The spread. So why do we need another notion called entropy? Well, I don't know. Let's figure out. Okay, so that's what we try to accomplish anyway. Right? So the measure of uncertainty of a random variable is what we call the entropy, and it's defined as such. Let x be a, so first let's consider the discrete setup. Okay, let x be a random variable, be discrete. Random variable. So discrete random variables, as we all know, is described by its probability mass function. Okay, so it takes value in a discrete set. Let's call it scripted x. A discrete set. The discrete set just means it's either finite or countably infinite. So you have a PMF, P of x, which equals the probability of big X equals little x. Okay, and little x is in the scripted x. Okay, I think we don't need to give too many examples of discrete distribution. Okay, this should be clear. So sometimes we also write. Sometimes we wish to emphasize this is a PMF for big X, so we write P subscript of X. That's also okay. Okay, so definition, entropy. Hx for the discrete random variable x is defined as the minus of the sum x in scripted x of p of x times the log of p of x. So here, p of x, because we're only dealing with one random variable, there's no source of ambiguity. This is just the PMF of x. So that's the definition. Here, because we notice there's a little bit of an issue here, because when p is 0, log would be 0. So you run into the notion, run into the term of 0 times log of 0. But 0 times log of 0 is defined as simply 0. What is information theory all about, my man? Oh, very good question. Actually, I'm not quite sure. So I just give this diagram, okay? It provides it provides a unifying perspective on so many different fields. It initially started out from communications theory. So for right now, I wish to understand information theory take on sufficient statistics. That's our goal. Okay? So right now, we're just introducing definitions. Perhaps it is not appropriate to talk about the big goal of information theory yet, because I'm not qualified to do so. Okay? So, but we'll get there. Don't worry. So here we have this definition of entropy in x, h of x. Entropy in x. All right, so there we go. As it was mentioned, you have a convention. We take 0 times the log of 0 to be 0. Technically speaking, this is undefined because log of 0 is minus infinity. Right? In fact, log of 0 is not even defined. So the reason we choose it that way, we choose to define it. Damn. Hold on. My mouse just died. I need to change my battery. Okay. Anyway, I'll be back in a minute. Too much intensive writing in recent days, so my mouse just died. Okay. Okay. Hold on a second. There we go. Okay, I'm reloaded. So 0 times log of 0 is 0, since we take that as 0, since the limit of x times the natural log of x. Oh, here, by the way, log, we always mean natural log, okay? As is usually the case in advanced mathematics. Limit of x approach 0 plus. We want to calculate this limit. Of course, this is an indeterminate form, 0 times infinity, so we use the L'Hopital's rule. So we rewrite this as the limit of x plus x goes to 0 plus log of x. Yes, this is originally the motivation. Thank you very much, Mark. Yeah, it has to do with data compression and redundancy and that sort of thing. Okay, so perhaps at some point we will have live sessions on reading classic papers. I think the original Shannon paper is still very much worth reading. Shannon was considered the originator of modern information theory. Okay, so now you use the L'Hopital's rule because this is infinity over infinity. So it's 1 over x over 1 over x squared. So this just simplifies to the limit when x approaches 0 plus minus x, which is 0. So when p is 0, the log is considered 0 times log is considered 0. Okay. So adding 0 probability term does not change the entropy. So if you have a term with p of x equals 0, that would not change the entropy, which makes sense. Because remember, h of x is supposed to measure uncertainty of a random variable. P of x equals 0, meaning x equals that value, x equals little x with probability 0. It's an impossible value in a sense. Okay, it's an impossible or a negligible value, so it does not contribute to the uncertainty of that random variable. Okay, so you can define this. You can also rewrite the definition as an expectation. So here it says, we denote expectation by E, big E. Definition, the formula. This is not a definition, but rather a formula. So if you have x follows the distribution, P of x, discrete, okay? So the function g of x, g is a function. G of x is a given function. The expectation of g of x. So expectation of g of x is written this way. And sometimes we emphasize the distribution of x. So we write a little p in the subscript of E. So just to highlight what distribution the expectation operator is using. So that would be the sum of x over scripted x, g of x times p of x. Okay, and sometimes if p is clear, you simply write another notation would be just expected value of g of x. Okay, you can suppress p if the distribution is clear. So as we can see, you can rewrite the definition of entropy as an expectation. So therefore, in this view, h of x is the expected value of 1 over, sorry, not 1 over, but minus log. But minus log, we know, is just the log of 1 over px. Okay, so so far we have two expressions which are completely equivalent. Okay, the nice thing about the expectation formula is is that we can use properties of expectation such as linearity. Okay, and it says this definition of entropy is related to the definition of entropy in thermodynamics. Some connections will be explored later, but probably not today. It's in a later chapter of the book, actually. And then it says it is possible to derive the definition entropy axiomatically by defining certain properties that the entropy of random variable must satisfy. Okay, and this approach is illustrated in problem 2.46. Actually, you know what? We will take a look at that. Put a note. Okay, remark. Axiomatic definition. So there's going to be some defining properties of the entropy without giving a formula. Okay, so in the axiomatic definition, we'll just say the entropy of a random variable should satisfy such and such and such, and from those definition, it will be possible to derive the formula. The axiomatic definition this is perhaps a more satisfying definition. Okay, so right now it just seems like a randomly given formula, which I totally the frustration of which I totally understand. Okay, but now let's just take that as granted and see what we can get from this definition. Axiomatic definition is in problem of the second chapter 2.46. Okay, so here it says we do not use the axiomatic approach to justify the definition of entropy. Instead, we show that it arrives at the answer to a number of natural questions, such as what is the average length of shortest description of the random variable? Okay, that's a very interesting question. It says what is the average? Okay, it is the axiomatic definition. And also, so the question to bear in mind is, quote unquote, what is, because this right now is still very vague, what is the average length of so-called shortest description? So it kind of encodes the idea of how complex an object is, right? Say if your random variable is just a constant random variable, the description would be very short. So there's very little entropy in it. That makes sense? But of course, it is not yet formalized yet. Okay, random variable. Okay, so now we have this definition, which right now seems rather unmotivated. That's okay. I always bring up this story taught by Sir Andrew Wiles, the guy who proved Fermat's last theorem. He said, in mathematics, when you do new mathematics, it's like you enter a dark room. It's like you enter a dark room and you walk around and you stumble upon furnitures. You get tripped over and over again, and eventually you recognize the structure of the room, okay, where each furniture is located, and finally one day you spend enough time in there and you find the switch, and now everything certainly falls into place. Okay, so still we're very much in the dark yet. So anyway, so the properties. So here we have the first property called lemma 2.11. First of all, entropy is greater or equal to 0. And this should be obvious because the negative log is positive. Right? So this is obvious. The proof is very short since p of x is between 0 and 1. Remember, p of x is a probability. It's between 0 and 1. So 1 over p is greater than 0, so the log of 1 over p of x is greater or equal to 0, and therefore h of x is greater or equal to 0, so we're done. If a random variable is non-negative, its average cannot be negative. Okay, so that's it. The entropy is non-negative. Okay, so now let's think about another. Here, the second proposition is a little bit weird, okay, which I'm certainly quite not sure yet. So it's just, the second lemma says 2.1.2, it says HB of x, okay, is what? HB of x is log B a h a x. Okay, so what does this mean? I think this refers to the base of the log is used. Okay, so here, I mean, we just take the natural log as its base, but the choice is perhaps inessential here. You can take, for example, you can take 2 base log. So if let's say HBx, where HBx denotes the sum. Actually, let's use the expectation formula. Expected value of log 1 over px, where the base of the log is taken as b. So there's that. Okay, that's the definition. So it says if you change the base from b to a, how are they still related? Right? Of course, that's just the property of the log. Right? It's just the property of log. So remember from high school algebra, there's a change base formula for log. So high school algebra says the log of p base b divided by log of a base b is log of p base a. This is base swap formula from high school. This is just a property of log. Okay, so if we write HB of x, which is the expected value of log base b 1 over px, and we change the base of the log, that will be the expected value of log a 1 over px times log of a base b, right? Yeah, just multiply this to the right. And then you take out the constant, so it's just log of a base b, and then times the expectation of this term, which is exactly h a of x. So that's just a change of base, so there's not much to talk about. Okay, so that means entropy can be changed from one base to another by multiplying the appropriate factor. Hopefully that's clear. Okay, and now let's take a look at the example. So the first example is, of course, the most basic discrete distribution, the Bernoulli distribution. So example 2.1.1. So consider x follows the Bernoulli distribution. That means x equals 1 with probability p. Okay, x equals 0 with probability 1 minus p. So what is h of x? Well, because it only takes two values, the sum is just two terms. So it's minus p log p and minus 1 minus p times the log of 1 minus p. There you go. So that's the formula for the Bernoulli random variable. It's just two terms. And let's give this formula a particular notation. Okay, this formula has a particular notation. It's called h of p, h of little p. Okay, so it might look a little bit confusing because previously the argument of h is a random variable. It is a functional. A random variable is a function, and h of x is a functional. It takes a random variable and returns a number. But here we're going to denote this expression, okay, the entropy for Bernoulli random variable as simply h of p. So this is just a real function of a real variable, a real valued function of a real variable. So the notation might look a little bit confusing. We're abusing h here. Okay, and by the way, I don't know why entropy is denoted as h. From the thermal books I've seen, entropy is denoted as S. I don't know why it's called H, but it shouldn't matter that much. Okay, so in particular, when P is 1/2, H P equals 1/2 is what? Let's calculate that real quick. This is minus 1/2 log of 2, log of 1/2 minus 1/2 log of 1/2. Okay, and of course now it really matters what base we choose. So if, say, the base is 2, then this will give us 1. If you use log base 2 as log, not the natural log, then you would get 1 here. Okay, and it is a easy exercise in elementary calculus to plot the graph of h of p. So I will skip the detail and instead just draw the picture right next to it. So when p equals 0, the first term is 0 by our convention. When p is equal 1, also by our convention, the second term is 0. Oh, actually, sorry, when p equals 0, the first term is 0 by our convention, and the second term is 0 because that's a log of 1. So when p equals 0, h of p is 0. And when p equals 1, And when p equals 1, the first term is 0 and the second term is 0 by convention. So the h equals 1 and 0 on both ends. And because of the symmetry here, it should have the maximum value attained at 1/2. The function concaves down. Once again, it's an easy exercise in elementary calculus to check. We might actually have to do that calculation later, but right now I'm just being lazy. Okay. Of course, the value of h depends on the base, but the shape isn't affected, right? The base only affects the scale. If you change the base by the previous lemma, the entropy simply gets scaled by a factor. So when you have h2, so when you use base 2, the maximum value is just 1, which is quite nice. So that's the shape of the HP. Let's think about why this measures the uncertainty in X, right? Because we mentioned from the beginning the measure of uncertainty of a random variable. So H, remember, what is the situation that we are most uncertain about a Bernoulli random variable? Let's imagine X is a result of an election. Okay, 1 means Democrat wins, 0 means Republican wins. In what circumstance are you most uncertain about the result of the election? Well, when P is close to 50%, right? So in that case, there will be a tight race. So there will be maximum uncertainty, which makes sense. If let's say P is very large, that means Democrats wins by a landslide, likely to win by a landslide. So nobody cares about election anymore because the result is already pretty much decided. And the same thing is true for the opposite direction, or the opposite scenario, right? So that's the intuition here. So P equals 1/2 gives maximum uncertainty. And let's compare this. Okay, let's compare this with a well-known formula. Compare this with another formula, the variance of X. The variance of X for a Bernoulli random variable is simply P times 1 minus P, which of course also have this behavior, which also have this qualitative behavior, is also have this maximized, it's also maximized at 1/2. The maximum variance is 1/4. So as you can see, the variance also measures the uncertainty, also captures the same idea. But why do we use why do we use entropy instead of variance? Perhaps later on there will be a perspective. Of course, variance has its own use, right? We talked about portfolio maximization, portfolio optimization in the mathematical finance stream. There we minimize variance. Okay, we chose variance as the main functional of the portfolio, but here we're just using entropy. Now, the reason of which is still unclear at this point, but let's see. Anyway, let's take a look at another example. This time the random variable is a little bit more complicated. Example 2.1.2. So now X can take on 4 values. So you can take A, B, C, D. Suppose they're all distinct, okay? Suppose these are all distinct values of random variable X. You're like mine of gold. Well, thank you so much. I don't know why, but I'm actually not that knowledgeable, okay? But yeah, this is as I said, this is like a community-driven learning experience, aka a seminar. Okay, just a fancy way of saying a seminar. Okay, with the probability of 1/8, and lastly you have X equals D with probability 1/8 as well. So that's all the possibility of X, right? And now let's calculate H. So why don't we take the log equals 2, okay? The log as base 2 from now on, okay? Because I said earlier, you use natural log, but it seems like from what I've seen so far, base 2 is used more often. So let's use base 2. Okay. Let's use base 2. So h2x here would be minus 1/2 times the log of 1/2 minus 1/4 log of 1/4. Something to bear in mind, it has nothing to do with the value of x. It only has to do with the distribution, which is quite interesting. On the other hand, the variance cares about the value. Perhaps that's a good thing to notice, right? We said variance cares about the variance. The variance is, in a word of applied mathematics, is not dimensionless, right? The variance is not dimensionless quantity. The variance, let's say, if x has a unit, if x is amount of money, like in portfolio optimization, x takes the dollar sign, or whichever currency you use, right? Then when the variance is minimized, you have actually no idea like how uncertain that is, right? So is $100 squared? Okay, so is $100 squared a large uncertainty in your portfolio? We don't know, right? It seems like the entropy is more suitable for analyzing uncertainty because it only has to do with probability values. The distribution function itself has nothing to do with the random variable value. Okay, that's perhaps an interesting observation. Let's continue calculating this expression. So you see, the values of A, B, C, D don't show up in the expression of the entropy at all. Okay, so just carry out this calculation. So you get, these are all base 2. Okay, so the first one is half times 1. The second is 1/4 times 2. The third is 1/8 times 3. And the fourth is 1/8 times 3. I simplify this fraction, seems to give what? That's 4/2 plus 2 plus 3. Okay, so 7/4. 7/4. And the unit is called bit. Okay, so that's the entropy of x for this particular distribution. You know what? I'm going to put a remark on the side in case I forgot later. So note how A, B, C, D is irrelevant. Plays no role. Play no role, okay? Play no role in the entropy. Which is nice because they can even be non-numerical numbers. Let's say ABCD stands for persons. Okay, so let's say now you have an election with more than one candidate. Okay, you have 4 candidates. Person A has 1/2 probability of winning. Person B has probability 1/4 of winning. C has the probability 1/8 of winning. D has probability 1/8 of winning. And you can still calculate the entropy. In this case, the variance would not even make sense. Because how do you add A plus B, right? It makes no sense. So this is once again the advantage of entropy compared to variance. Unlike variance, ABCs don't even have to be numerically valued. And it's also dimensionless. So that's pretty nice as well. All right. So, and the text continues, okay, which I will just put the paragraph on screen. It's not a big deal. So suppose we wish to determine the value of x with a minimum number of binary questions. Minimum number of binary questions. An efficient first question is x equals a? It says, efficient first question is x equals a. It kind of makes sense, right? Because a has the largest probability. Remember, there was a question posed earlier. What is the average length of shortest description of the random variable? The average length. Okay, so the efficient first question is is x equals a. This splits the probability in half, right? Because x equals a with half probability, x not equal a with half probability. If the answer to the first question is no, the second question can be is x equals b. And then you split the remaining 50% probability in half too. And the third question can be is x equals c. Right? The resulting expected number of binary questions required is 1.75. So that's pretty cool, right? So now you have an interpretation of this calculation. 1.75. So like how on average, how many questions is needed to decide the value of x? Right? So let's say I was saying that x is the result of an election. And there are 4 candidates. Right? You miss the news and you ask somebody who watched the election, watched the vote counting process, and you wanted to know who won the election. Of course, you start from the most likely candidate, A. So go ahead and ask, did A won? Right? If not, then you go down the list according to descending probability. Right? So, and if you follow that format, the expected number of binary questions required is 1.75. And this turns out to be the minimum expected number of binary questions required to determine, hold on a second, this turns out to be the minimum expected number of binary questions required to determine the value of x. Okay, so later on, apparently there's a interesting result down the road. It says, in chapter 5, we will show that the minimum expected number of binary questions required to determine x lies between hx and hx plus 1. So now, here we calculated h2x. It happens to be hx, right? The minimum number required. Actually, you know what? Why don't we just calculate that? What is 1.75? How does it? Because is the calculation process identical? I'm not sure. Let's verify. Let's verify. Okay. So, like, given this procedure, given this questioning procedure, let's calculate the expected length. So let's suppose, given this questioning procedure, let big N be the number of questions asked. Questions needed, okay? So N is now a function of x. N is now a function of x. Why? Because let's say here, x can be a, b, c, d. And this is N. If A1, you just need 1 question. If B1, you need 2. If C1, you need 3. And if D1, you need 4. There's that. Right. Given this questioning sequence, the number of questions needed is determined by x. Okay, and what's the probability? Well, 1/2, 1/4, 1/8, 1/8. And what's the expected value of n? Easy. Just 1 times 1/2 plus 2 times 1/4 plus 3 times, hold on a second, 1/8. Oh, actually, you don't need the last one. You don't even need that. Because sorry, here I made a mistake, you see. It's not 4, it's 3. Because if all 3 questions are negative, then D must 1, right? So you don't even need to ask the 4th question. That's redundant, so it's just 3. So regardless of the answer you get from the third question, you know the answer. So there you go. And here, as you can see, the expression happens to be the same as the last one. And perhaps this is just a coincidence that it turns out to be the same as h of x here, which is 1.75 bits. We haven't shown that, okay, this is actually the minimum yet. In theory, I know information. In practice, yeah. So I guess, I mean, we just did this calculation. We said, okay, that's the questioning sequence. You can calculate n rather easily, but we haven't shown this is actually the minimum expected number of binary question required. We don't know. It feels intuitive that way, but we don't know this is a minimum. And it is promised here that in chapter 5 we'll take a closer look at it. Right. So anyway, so that's section 2.1, the definition of entropy. Hopefully after that we get an intuitive idea of why this is defined, how this is defined, and why we don't use other metrics such as variance to measure uncertainty. Okay, and now let's take a look at the second section. It's called joint entropy and conditional entropy. So things are getting more interesting now, because previously it's just one random variable. So joint entropy and conditional entropy. And I think this has to do with the sufficient statistics, which Leo mentioned last time, and I'm very much interested in. Okay, so definition. So let's say you now have a pair. Let x and y be jointly distributed. Discrete random variables. Discrete random variables. So both are discrete. With PMFs, joint PMFs. Okay. With PMF, let's say, of course, joint PMF, let's review that. P of x and y is big P, double strike. You see, this is the problem with probability theory. The letter P is overloaded. Big X equals little x, and big Y equals little y. So that's the joint PMF of bivariate discrete distributions. Okay, so now you can define the functional h of x and y. Yeah, we're getting there, Leo. So h of x and y. So this is defined as the negative of the sum of little x in scripted x, the sum of little y in scripted y. Okay, so these are the support of x and y respectively. The values that big X and big Y can take respectively. Okay, and then times pxy times the natural log, or not the natural log. Here, I think in information theory we use base 2 log by default. I've mentioned that a few times. All right, so there you go. So that's the definition of the joint entropy. Right, this is a joint entropy. The joint entropy of course, the joint distribution. There you go. And of course, you can borrow the notation from probability theory and write that as an expectation. So that would be the minus of the expected value of log p big X big Y. So now you're treating the log of px, py as a random variable. A lot of places you get log e factor and just working with natural log helps. I see. You still use natural log. Okay, great. I see. I see. Perhaps it's easier to do calculus. That's why. It doesn't really matter because it's just a scale factor. It is unique up to a scale factor. All right. So that's the joint entropy. Let's box that. Nice definition. And see what consequences can we derive from this definition. Okay, cool. Pinskers inequality. Anyway, so we have the joint entropy. Let's now define the conditional entropy. We also define the conditional entropy of a random variable given another as the expected value of entropies of the conditional distribution, averaged over the conditioning random variable. All right, so that's the joint entropy as we just defined. Let's continue definition. If xy follows the joint distribution px and y, the conditional distribution, the conditional entropy with the notation h y given x is defined as follows. Okay, h y given x here. This is defined as the summation of hold on a second. This says the summation of p of x times h y given big X or equals x, huh? What the hell? Because this looks very different from what I expected. Okay, so that's the definition. So let's work with that. This is defined. Okay, this is defined as, you see here. We don't know what this is yet. Okay, we don't know what this is. So let's keep expanding. The h of y given big X equals little x is defined as follows. So first of all, you need a minus sign at the front. You need a minus sign at the front here, and x over big X, p of x times the sum, okay, of okay. I'll keep writing and perhaps we'll do some reorganization because I'm a little bit confused. So this is what the text says. So the h of y given big X equals little x is minus the sum of y in big square y of the conditional distribution p y given x times the log of p of y given x, apparently. Okay, and now if we bring the two summations together and notice what's the product of p of x times py of x, right? That's just the joint distribution. Recall the definition of conditional probability. So, recall, conditional probability. So if you have A, B are events with PB non-zero, then PA given B, the conditional probability of event A given B is the probability of the joint event A and B over the probability of B. Let's recall what's the intuition for that. So imagine you have a sample space, big omega, and A and B are events. So this is A, and this is B. So now imagine B already happened. The idea of A given B is that B already happened. We know that B happened. What's the probability of A happening? Well, if B already happened, then the sample space is now restricted to just B. Right? Everything outside of B is now irrelevant. So within this restricted new sample space, what's the probability of A occur? Well, you just use the size of the joint event. You take the ratio between the size of the joint event and the size of the restricted sample space B. Right, so that's the definition of conditional probability, and for that reason, the conditional distribution is defined in this exact same way. So the conditional distribution of y given x is the joint distribution p of x and y divided by p of x. Right. So you always use the joint distribution divided by what's being conditioned on. So now let's notice you have p of x times the conditional distribution, which gives you the joint distribution. So that's just the p of x, y, x and y, p of x and y. And then taking the log of the conditional distribution, the log of the conditional distribution. So in probabilistic notation, this would be the negative of the expected value of big log y given big X. Sorry, P of y given big X. Okay, interesting. I hesitated when I was writing this derivation, even though now I think I have a better idea. Still, let's re-walk through this. The reason I hesitated is because I keep thinking about the definition of conditional distribution or conditional expectation. Remember, compare this, okay? Compare this with the definition of conditional expectation. There seem to be some quite significant differences here. Yeah, so recall conditional expectation. Right, what's conditional expectation of y given x? Well, first of all, it is a function of big X. So this in itself is a random variable. Conditional expectation is a function of big X, which is a random variable, because X is a random variable. It's a function of big X, a random variable. So here, h of y given x should be a number. You see, here the double sum leaves no free indices. The double sum leaves no free indices. X and y both sum over. This should be a number. Whereas h of y given x is just a number. So this is something I might need to spend some time getting used to. Right? Just to be clear, what's the definition of conditional expectation? So first of all, let's consider a different notation. So y given big X equals little x, yeah, all indices are in sum jail, right? They're all summed over, so nobody is free. So here you get, this is the summation of y times y given x. So in this definition, x is fixed. It only sums over y. So that's why I was like, oh, wow, hold on a second. We're summing over x? What's going on? X is given, right? So now it seems clear that why I was confused. So h of y given x is a number, whereas expected value of y given big X equals x is a scalar. sorry, this is a function. This is a function of x, a function of x. So there's that. And this is perhaps nice to know, but not essential, that the conditional expectation, this is a function of x. You can simply write it as g of x, okay, g of little x. And then the second notation, which is expected value of y given big X, is just the same function g, and the inside little x is now swapped to a random variable big X, which is a random variable. And the g function up and down are identical. Okay? So just as a quick example, as a review of conditional expectation, for example, say you're dealing with a random sum. This is a classic example. Say s equals x1 all the way, x1 plus all the way to x big N. Okay, xi's are ID, each with a mean mu x, which is also independent of big N, the number of terms, which is also random. And this is why it's called a random sum. It's used in insurance mathematics. So imagine each xi is the amount of claim, and you have n cases which you don't know in advance. You don't know how many cases you would receive in future, right? So here n is also random. Let's consider xi is independent of n, okay? And n with mean mu big N. So yeah, Leo was saying that in this summation, no index is free. They're all summed over. So eventually just get a number. My confusion was, because I come from a probability background, so this notation, e of y given x, is considered as a function of big X. So there's that. So let me just give an example of a conditional expectation. This is very easy. So if we condition on the number of terms, so the expected value of s given big N equals little n is just the expectation of a sum with fixed number of terms. Right, so that's very easy. So that's just expected value of x1 plus all the way to big Xn, given that big N is now little n. Since big N is now little n, you can substitute and you get expected value of x1 plus all the way to big little xn, and you have n equals little n. And notice now here at the front you have no big N anymore. Because of independence, the condition can now be dropped and simply write expected value of x1 plus all the way to little xn, which just n times mu x. So as you can see, this is a function in little n. Let's call that g of little n. And if we switch notation to expected value of s given big N, okay, that would just be g of big N. G of big N, of course, is just big N times mu x. It's a linear function in big N. So you see, that's why I said the conditional expectation is a function of big X, a random variable. This is a random variable, and you can calculate mean and variance for that matter. Okay. And just as a side note, perhaps useful, conditional expectation is also an L2 projection. So conditional expectation is an L2 projection. That is to say, So here, this is the subspace, which are functions of x. So overall, x and y together lives in the space L2. Imagine. Okay, so consider these are all imagine. So they are considered as L2 random variables with finite second moment. And now you have a subspace. This is a subspace of random variables that are L2. Okay, that are L2 which are dependent on x. Okay, I'm bypassing measure theoretic notation. So basically, you can consider this plane I just drawn is the subspace of L2 that only depends on x. Right, L2 Hilbert space. Okay, yeah, Leo Lecter is also L2. Leo Lecter, you might want to join the L2 league of the membership of this channel. Anyway, here, so you have a vector y. A vector y, the orthogonal projection of y onto the subspace is exactly the conditional expectation, which I made a video about a while ago. So conditional expectation is also a matter of orthogonal projection in the L2 setup, okay, which is quite applicable. Okay. Conditional expectation is also L2 projection. And identities about conditional expectation can also be derived from this geometric perspective. Beautiful. All right. So that's the difference between the quantity hy of x, hy given x, and the conditional expectation. And speaking of which, you see here, h of y given x equals little x is something different, right? Here, in our discussion, I mentioned when it comes to conditional expectation, e of y given x and e of y given x equals little x are completely the same thing. They're just the same thing. It's the same function g. Right? If you wanted to treat the argument of g as a random variable, boom, it's a random variable. If you want to treat it as a deterministic, that's a deterministic. But the function g is the same. But here, as we can see, h of y given x equals little x is different from h of y given big X. So these two are not the same thing. Okay, so from this derivation, it is clear that, let me just put it here. So this was the derivation we did. Okay, these are all equivalent definitions. These are all equivalent definitions of the conditional entropy. So here, h of y given big X equals little x is what? Is this thing with a minus sign. So this is minus the sum of p y given x times the log of y given x. Log of p y given x. And you sum over y. Sum over y. So what is that? Well, here actually we treat x as a constant. Here we actually treat x as a constant. So this is what? This is the expected value of log 1 over p of big Y given little x. Okay, and you're using the conditional distribution. So there's that. So probabilistically, perhaps, you know what, we don't write this in probability, but basically in probability theory, we write this as, using the notation I just used, this is the conditional expectation of log of 1 over big Y given x when big X is equal to little x. Take a look at the definition. Here, P, y given x are the same. And the function, instead of y, is now treated as log of y given x. Y is being summed over. So the point is, this is a function of x. Because here you only have one summation. There's only one summation, so x is left as free. So this is a function of x. Let's just denote that as, say, phi of x. This is a function of x. This is a function of x, whereas h of y given x without the little x, without the little equal x at the end, is a number. There's double sum. Okay, so this is perhaps the most disturbing distinction. Okay, I imagine I'll spend quite some time trying to reconcile them. But I mean, the definition itself is clear. It's just that it's in conflict with the existing knowledge. I mean, notational wise, there's no logical conflict, but basically you have to get used to that. Okay, when I was trying to not look at the book and write down this definition, I'll figure out. I figure out you sum over y here. I thought you just at the first step you just treat x as a fixed number, and then you sum over y. Okay. So yeah, this is a function in x, whereas as I mentioned here, this is a number. Oh, let me drink some water. Ming, do you see yourself more as a Batman figure or as a Spider-Man type? Probably Spider-Man, huh? Because I'm not rich. Okay, that's interesting. So yeah, the first one is a function of x. This one kind of looks like it's closer to this quantity is closer to the conditional expectation. But this is a number. Okay. I guess now it's time to do some examples. And actually, before we do that, let's try to interpret what is going on here. Oh wow, you're making slides for tomorrow? Thank you so much, Leo. I just write everything from scratch from like the this is my whiteboard. Thank you very much, Leo, for your preparation. Yeah, see you. Thanks for joining the stream. That's awesome. All right. So what we're doing here is let's think about what is the meaning of this. All right. So first of all, well, I think we are pretty certain about the meaning of this one. H of y given big X equals little x is simply the entropy of the conditional distribution. Right? Conditional distribution of y given x is a distribution that depends on x. So it is natural that the uncertainty in that conditional distribution also depend on x. But now x is also being summed over. But that's also being weighted according to P of x. So here, this little h here, I was saying, h of y given big X equals little x is just the entropy of a single random variable. Just a single random variable. So x is now no longer random. This is considered constant. This is the uncertainty of the conditional distribution. of the conditional distribution y given big X equals little x. That's the uncertainty of the conditional distribution, which depend on x. And now the conditional entropy, okay, this is quite important. Conditional entropy is not the entropy of the conditional distribution. That would be very naive. Right? So this is the uncertainty slash entropy. The entropy slash uncertainty of the conditional distribution. H big Y given big X without the little equal x at the end, right, is the average entropy. You see, this is being weighted by the P of x. So this is the average entropy of conditional distribution. That's the previous expression is the entropy of the conditional distribution given x, which of course depending on x. Here, the average entropy of the conditional distribution averaged over x, which is a number. You see the difference here? In the conditional expectation, those two are the same thing. It's just the same function, different interpretation. Here, the calculations are different. When it comes to h, the two calculations are different. Okay, so perhaps if you come from a probability and stat background, this is quite important to pay attention to. Okay, so hold on a second. Do we have example? Okay, let's do the example. Before we prove theorem, let's do example. Example 2.1.1. So suppose you have the joint distribution. Let me just gonna put the table here. Okay. So there you go. That's the joint distribution. Suppose you have this joint distribution. Let's see what are the quantities we just defined. So the table is the table for P of x and y. This is P of x and y. Let's calculate the joint entropy, shall we? Well, by the last expression, here, let's first calculate the joint entropy, then calculate the conditional entropy. The joint entropy is clear, right? That's just the uncertainty in the joint distribution. But the conditional entropy is not the entropy in the conditional distribution. The conditional entropy is the average entropy of the conditional distribution. Very subtle. All right. So first, let's take the log. Right, this is P of x. Let's take the log. Put in the table. Perhaps that's a good way to write it. So here, this is another table, log of pxy. All right, so x and y still take these values, 1, 2, 3, 4. They don't matter. What matters is the probability values, 1, 2, 3, 4. Okay. Actually, you know what? Let's take the minus, just to avoid negative numbers. So 3, 4, 5, 5, 4, 3, 5, 5, 4, 4, 4, 4, and Here you have 2, infinity, infinity, infinity. Okay, so there's that. H of x, y. H of x and y, the joint entropy. Well, it's just the sum of corresponding, the sum of products of corresponding entries. So it's like 1/8. It should be 16 terms, okay? So 1/8 times 3 plus 1/16 times 4 plus 1/32 times 5, 1/32 times 5. So that's the first 4 terms, and then you add the rest. 1/16 times 4 plus 1/8 times 3 plus 1/32 times 5 plus 1/32 times 5. Okay, keep going. Then you get 1/16 times 4. Okay, evaluating the expression is not that interesting, but it's a good practice for the definition. Okay, 1/16 times 4. These are all identical terms. 1/16 times 4 plus 1/16 times 4. All right, and then plus 1/16 times 2 plus 3 zeros at the end. 0. Okay. So to try to evaluate this, okay, let's calculate that. Okay, it's tedious, but shouldn't be too difficult. Okay. Hang on. This is what? This is 32. The first row. Okay, first row you got 32 times 3 times 4 is 12. 2 times 4 is 8. And plus 10. All right. So that's 30/32. The first row. Looks okay. The second row would be something over 32. First one is 8 and plus, oh, it's the same. It's the same. Hi Gilbert. Thank you very much for joining the stream. I'm good. So that's 30/32. Right? So, and here this was just is just 1. The third row is just 1, and then lastly you get 1/8. So you add them together. These two add together, you get 32 at the bottom and 60 on top, which is 15/8. 15/8, and then you get in total you just get 3. So 3-bit, the unit of entropy. I mean, it doesn't have a unit. It's dimensionless, but we just attach like a bit at the end. It's like hertz, right? Hertz is the unit of frequency. Of course, frequency on its own is dimensionless. Okay, so that's the joint entropy, which is easy to calculate. Actually, you know what? Let's calculate as a review for the previous section. Let's calculate the what's that called? The entropy of individual random variable, the entropy in x and entropy in y individually. I mean, we need the marginal distribution anyway, because we need the joint. Sorry, we need the. Hold on a second. What's that? We need the conditional distribution. Okay, so let's calculate the marginal distribution. Marginal distribution for x and y. So if we just care about the probability of y equals 1, 2, 3, 4, and so on, no, just 1, 2, 3, 4. Okay. There's no such thing as so on. Okay, so on the probability of y equals 1 is the sum of the first row. So 1/8 it's 1/8 is 4 over 32 plus 1/16, that's 2 over 32. So you get 6 over 32, and then eventually you get 8 over 32. 8 over 32 is just 1 over 4. That's just 1/4. Okay? The first row sum up to 1/4. 1 over 16 is 2 over 32. 2 over 32 plus 1 over 8 is 4 over 32, which is 6 over 32. And then plus, it's the same business. It's the same. It's still 1/4. And finally 1/4. Oh, it's a uniform distribution. Why is a uniform distribution? So why is a uniform distribution? This means hy is very easy to calculate. So that's just 1/4 times the log of 1/4, negative log of 1/4 plus minus, okay, the 4 identical terms. So, well, so therefore you just get log of 4, which is 2-bit. Okay, and let's do the entropy in X. Okay, so the total for X, total probability for X. But I'm new to higher mathematics, studying group theory right now on my own. Where should I recommend go from there? I don't know much about group theory. That's the problem. Okay, I mean, my background in algebra is very weak. Where I recommend to go from where? I guess you can, yeah, join my Discord server and ask for advice there. Okay, I'm next to illiterate when it comes to abstract algebra. This is not a joke, because if you go to my 2.0 channel, just search Math with Ming 2.0, you will see live on me studying abstract algebra for the first time. There's really not much I can comment. But the thing is, you know, the method of studying mathematics, as showcased in these live streams, are pretty much transferable. The process, okay, that is, you try to make connection with past knowledge. You work out examples, problems, and do the proofs. It's really just that, of course. And of course, when it comes to the specific goals, let's say you wish to study a specific algebra subject. Okay, so let's say if you want to study group theory for a particular application, so let's say you want to study group theory for physics, you need some expert advice. Yeah. If you just wanted to study group theory because it's interesting, then you can pretty much go with the flow of any textbook, right? But if you have a specific goal, it's better to consult advice from experts or just someone more experienced than you, right? Okay, so let's move on. The total probability for x equals 1 is the sum of the column, the first column. So 1/8 is 2 over 16 plus 1 over 16 plus 1 over 16, that's 4 over 16. 4 over 16 is 1/4 plus 1/4 is 1/2. Yeah, looks about right. Sorry, next. And then you get 1/16 plus 1/16 is 1/8. 1/8 plus 1/8 is 1/4. This is 1/4. And 1/32 plus 1/32 is 1/16, and then plus 1/16, that's 1/8. And this is just 1/8 again. Yeah, no worries. So hy, this is h of y. So we just calculate h of y. So now let's calculate h of x. So h of x is minus 1/2 log of 1/2 plus 1 minus 1/4 log of 1/4 minus 1/8 log of 1/8 minus 1/8 log of 1/8. So this is, there you go, you get half times 1 plus 4 times 2, 1/4 times 2, plus 1/8 times 3. Okay, and then plus 1/8 times 3. To simplify that. So it's 1 plus 1/2, 1.5. And this is 6/8, that's 0.75. So that's 2.25, huh? 2.25. There doesn't seem to be an obvious relation between hy, hx, and h of x and y. Perhaps because we never take into account of their correlation. Okay, so anyway, so that should be the answer. For just to double check, okay? Just to double check. So this is 3/4. Together you got 5/4. 5/4 is 1 point. Did I make a mistake? I think I made a mistake. 1.25 plus the 0.5, which is 1.75. Okay, 0.5 plus 0.5, yeah. Yeah, so it's 1.75. I made a arithmetic mistake. 1.75. Gotta double check. Okay, anyway. So this is 1.75. That's h of x. So now comes the big quantity of interest, which is the conditional entropy. Right? So I will calculate the conditional entropy of x given y. And I'll leave an exercise for you to calculate the conditional entropy of y given x. How's that sound? So, to calculate h of x given y, we first need the entropy of the conditional distribution. So that is h of big Y equals little y. We first need this function of little y for y equals 1, 2, 3, 4. Remember, this is just the entropy of the conditional distribution. So we need to calculate conditional distributions. Okay, so here we have this table for the joint distribution. Let's just use this format and calculate the conditional distribution. So we need to calculate conditional distribution. The conditional distribution is px given y, which is the joint, divided by the marginal. Okay. Given y, what's the distribution of x? So each row is now a distribution on its own. Each row is a univariate distribution on its own. So it's 1/8 divided by 1/4, 1/16 divided by 1/4, and so on. Okay, so let me just copy this format. Okay, so I'll put this on the side at the moment. Okay, I would just calculate the conditional distribution right next to the joint table. This way is easier. So here, the table is now the conditional distribution of x given y, p of x given y. Okay, and I'm going to erase all the entries here and only leave the headers. The conditional distribution of x given y equals 1 would be 1/8 over 1/4, that's 1/2, and then 1/4, 1/8, 1/8. Okay, so you know what? I will add another column to it. Okay, the other column is the entropy of the conditional distribution, the h of x given y equals little y. Okay, y equals 1, 2, 3, 4. I want to calculate these things on the side. So let's continue. We'll do that later. But first, let's calculate the conditional distribution in each row. There are 4 conditional distributions in total. Okay. So 1/16 over 1/4 is 1/4. 1/18, 1/8 over 1/4 is 1/2. 1/4. 1/8. Sorry, 1/8. 1/8. Done. Okay, and now you have 1/4, 1/4, 1/4, 1/4. Uniform distribution. And the last one is deterministic. The last one, when y equals 4, x can only equal 1. So that's deterministic. Okay, and now let's calculate the entropy. Can we do that in our head? Well, the entropy of the first distribution, this is one distribution. This is a conditional distribution. Given y equals 1, that's one distribution. Calculate the entropy for that would amount to 1/2 times log of 1/2 plus, actually, you know what? Let me write down the formula because now we're still in the very early stage of this study. Bummer, I left my copy at work. What copy? The textbook? You can just Google it. Okay, and Douglas, if you're talking about the textbook, I mean, I will write down all the relevant information, of course. But if you want to have a copy on the side, which is optional and recommended, okay, it's optional but recommended, then you can just Google it. There should be the relevant link. Okay, let's just leave it that way. Okay, so here, the first row gives you h of x given that y equals 1. 1/2 times the log of 1/2 plus 1/2 times the log of 1/4 plus 1/2 times the log of 1/8. Did we calculate this before? Because these numbers seems to be used quite a lot. Yes, exactly here. Oh, actually, I forgot the minus sign. That's a bad mistake. Entropy should be non-negative. And indeed, we came across this expression earlier. Here. Oh, actually, I made a mistake. This is second factor is 1/4. Oh, this is 1/8 as well. 2 more mistakes. My bad. Yeah, it's the same here. It's 1.75. So this is 1.75. Right? And the second row is the same because it's just the same probability. The values don't matter, remember. The values for the entropy don't matter. So even though if you change the values of x, it doesn't matter. It's the same expression. 1/4 times log of 1/4. Sorry, minus 1/4 times log of 1/4 minus 1/2 log of 1/2, blah, blah, blah. All that business. Okay, here you have what? Uniform distribution with probability 1/4. We calculate the entropy for that. That's the entropy of y. That's just 2. And the last one, okay, let's write that down. H of x given y equals 4. Is that a 0? Yeah, I believe that's 0. So it's minus 1 times the log of 1. And then plus 4, 0. Plus 3, 0. So it just gets 0. That makes sense because this is deterministic, so there's no uncertainty. Entropy is 0. So kind of reinforce the notion that entropy measures uncertainty here. All right, so that's a 0. So we have that, and now to get the final answer, h of x given y, you need to average all of these values according to the probabilities of y. Right, so let's write that down. That's the summation over the values of y times p of y, the probability distribution of y, and then times what we just calculated, the entropy of the conditional distribution when y is fixed. Now, this is the average entropy. This is the average entropy of the conditional distribution. So you calculate the entropy for each conditional distribution, and then you average them. Okay, so the distribution of y happens to be uniform, remember? So it's just 1/4. So literally that's the arithmetic mean of the 4. So 1/4 times 1.75 plus 1/4 times 1.75. That's a special case, of course. In general, you use the you just use the probability. If it's unequal, then it's unequal. It doesn't matter. Okay. All right. So there you go. 1.75 times 2 is 3.5. 3.5 plus 2 over 4. That's the answer. 5.5 over 4, right? Which is, okay, to the elementary school arithmetic, 1, 4, 1, 5, 3, 2, 3, 0, 7, 5. 1 point. So the answer is 1.375 bit. Right. That's the average entropy of conditional distribution of y of x given y. So that's the number. Whereas h of x given y equals to y is a function. The table is right here. When y is 1, the value is 1.75. When y is 2, the value is 1.75, blah, blah, blah. Okay. So hopefully that cleared up the concepts a little bit. Okay. So far we're just following the definitions and doing some calculations. Okay. And as an exercise, calculate h of y given x following the method we demonstrated earlier. Okay, yeah, just a straightforward application of the definition. Just need to be a little bit more careful. Okay. Okay. So all right, that's nice. Okay. I mean, at this speed, we're probably not going to get to sufficient statistic, which calls for a follow-up stream. But I'm okay with that, right? It's better to be, how should I put it, to be safe about what we learn than pursuing progress at any cost. Okay, so now we think we don't have, so to say, a natural understanding of what these means, but at least we can operate these notions. Okay, so now we've seen an example of these definitions. It's time to do some proofs. Okay, what are the results, the fundamental results? And here we have a fundamental result, actually. A big theorem. The first big theorem in information theory. We only so far have seen a bunch of definitions. Here we have a theorem. This theorem 2.2.1 in the text is called the chain rule. Of course, it's not the chain rule in calculus. And let's take a look at what's the statement here. The chain rule says the joint entropy h of x and y is h of x plus the conditional entropy h of y given x. Important formula. Okay? So that's pretty nice. So that's pretty nice. So think about the meaning before we prove it. Okay, what does this say? Perhaps it's instructive to rewrite the expression as h of y given x equals h of x and y minus h of x. So it's like you have h of x and y to measure the uncertainty in the joint distribution, and then you subtract that by h of x. That's the uncertainty in x. You get what? You get the conditional. You get the conditional entropy. The conditional entropy, as mentioned, it is the measure of the average entropy in the conditional distribution of y given x. So by conditioning on x, certain uncertainty is lost. Right? That's the idea. On average, this is what the amount of uncertainty left. So that's pretty cool, right? Conditioning on x removes uncertainty. And by how much? Well, this is what remains. This is called the chain rule, apparently. All right, so let's do the proof. I think the proof is just a straightforward computation. Okay, so let's start with h of x and y, the definition of h of x and y. The uncertainty in the joint distribution. So that's a minus sign, sum of little x over script of x. Actually, you know what? Just write sum over x. That's already enough information. Sum over y, p of x and y times the log of p of x and y. All right. So we need to cook up a conditional distribution somehow. So perhaps it's useful to use the definition of conditional distribution. So write the second joint distribution as the conditional distribution times the marginal distribution. So you get the sum over x, the sum over y, p of x and y, all that business, times the log of p of x times the conditional distribution y given x. Right, yeah, we're interested in y given x. Of course, use the law of logarithm. The sum now breaks into 2. So you get the minus sum over x, sum over y, p of x and y, times the log of p of x minus the sum over x, the sum over y, p of x and y, times the log of the conditional distribution, which is p over p of y given x. All right? So there's that. Okay, so let's see what happens here. Well, in the first sum, in particular, notice how log of p of x can be taken out of the summation over y. So minus sum over x log of p of x. Because this has nothing to do with y. And then sum over y of p of x and y. That just gives you the marginal distribution of x. So this is exactly p of x. Okay, and then let's continue writing the second term. Well, the second term is already clear, right? The second term is already here. Is already the conditional entropy. This one right here. So it's already h of y given x. So we're pretty much done. Okay, and here I'm saying that this is sum over x log of px times px. Plus the conditional entropy, and this is h of x plus h of y given x. QED. All right? So that's done. Okay, so that's the chain rule. That's the chain rule, and you have a shorter proof makes use of the expected value. Shorter proof. Shorter proof says, well, here h of x and y. Remember the definition is the expected value of negative log of p of big X and big Y. All right. There you go. And the entropy in one random variable x is the expected value of minus log of px. There you go. And lastly, what's the joint? Well, the conditional y given x. That's the expected value of minus log p of y given x. So these are all just definitions, right, in expectation notation. But because since you have a log of the joint is the log of the marginal plus the log of the conditional. And then you take expectation and use linearity and you're done. Take expectation, use linearity of E, and we're done. That's a much shorter proof. So you see the advantage of using the expectation notation. Okay. So that's the chain rule. I think we can move on from now. All right. So is everything clear so far? In particular, regarding the definition of conditional entropy, which in my opinion is perhaps the hardest concept so far. All right. So here, as I was mentioning, as I was saying, the result, I asked the viewer to calculate. I've asked the viewer to calculate the h of y given x, right? H of y given x. So you should observe that h of y given x is not the same as h of x given y. They're as expected. There's no reason that they should be the same. It should be the same. However, there is a property that relates the two. There's a property that relates the two. There's a so from this chain rule, it is clear that because h of x and y is hx plus h of y given x. This is also h of y plus h of x given y. So they are related by this equation, right? Which is equivalent to h of x minus h of x given y equals h of y minus h of y given x. So that's a nice little symmetry going on. The textbook remarked that this is going to be an important property that will be useful. Okay, so let's just put that, okay? You will be useful. Okay, why don't we just verify the theorem, the chain rule from the previous example? Do we have that? H, x and y, that's 3-bit. Hx is what? Hx is 1.75. So do we calculate? Oh, actually, I didn't calculate h of y given x. Huh. Okay. But anyway, I did calculate h of x given y. So this is h, h of the joint. H of y is 2, which means h of x given y should be 1, huh? What? Hmm. What is going on? So something is wrong here. Because actually, guys, this is the example in the textbook. Oh, actually, in the textbook, the textbook says I made a mistake here. The joint is wrong. The joint should be 27 over 8. Let's re-verify this again. Okay, so something is wrong with the joint entropy. Something is wrong here. Okay, so let's recheck. So here you have 1/8 times 3. First check the expression. Okay, 1/16 times 4, 1/32, 1 over 32 times 5, 1 over 32 times 5, 1 over 16 times 4, 1 over 8 times 3, 1 over 32 times 5, 1 over 32 times 5, blah, blah, blah. These are all looks okay. So somehow I made a mistake here. You just spot that. So this is 32 at the bottom, 10 plus 8 plus 12. Second row is the same, so that's what? That's 32, about 30 on top. Is 16 on the bottom, 15 on top. 15 over 16, that's just 1. And finally, you have 16, 2 over 16. All right, so that's what? That's 30 over 16. Over 16, that's 16, 30 plus 16 plus 2, which is 48 over 16. Okay, sorry guys, I need to use the bathroom real quick. I'll be back. Okay, so still this is messed up. This is supposed to be, okay, this is supposed to be, if you guys want, you can check, this is supposed to be 27 over 8, not 3. Okay, I'll be back. Silly algebra mistake. All right. Oh, here I'm back. Oh, nobody left? Oh, that's amazing. Okay. Thank you guys for waiting. So, there's some silly mistake just is done here. I am not sure where. So, is there any eagle eye in chat that can help me out here? Of course, it's completely my fault. This is what? So, yeah, 48 over 6, that's 3. Damn, what's going on? Did I mess up the table? 1 8, 1 over 8 times 3. Okay, recheck the definition. Yeah, this is all right. Oh, here I think I made a mistake. This is 1/4, right? This is 1/4, but that shouldn't matter too much, huh? But actually, it shouldn't matter. What am I talking about? This is 1/4, not 1/16. I copied it wrong. Okay, so redo the calculation. The two first rows are 15 over 16, 15 over 16. So together you get 30 over 16, which is 15 over 8. 15 over 8 plus 1, that's 23 over 8. And then, yeah, then you plus 4 over 8. 4 over 8, that gives you 27 over 8. Yeah, indeed, 27 over 8. Silly mistake, because I copied the probability 1/4. I didn't, this one was wrong. Okay, anyway, doesn't matter. This it's annoying, but now it's fixed. So it all should now work out. Let's convert that into decimals. Convert that into decimals. So here you go. H is 27 over divided by 8. That's 3, 24, 3, 0 times 3, 24, 6, 0 times goes up 7, 56, 4, 0, 5. 3.375. 3.375, that's the joint entropy. Okay, great. And now let's verify. Is the chain rule true? Is the chain rule verified here? Yeah, 1.375. 1.375 plus hy is hy of x. So indeed, in the example, okay, h of x, y, this is 3.375 equals 2 plus 1.375. 2 is h of y. See, 2 is h of y here, and 1.375 is h of x given y. Okay, and of course, this should be the same as hx plus h of y given x. We calculated hx, didn't we? We did that. Hx is 1.75. 1.75. So hy of x should be 3.375 minus 1.75. Okay, so it should be 1.625. Even though we didn't calculate that explicitly, you should independently verify. The answer should be 1.625. And they're not the same as the entropy of x given y. Okay, not the other conditional entropy. They're not the same. Okay, so far so good. We have the first theorem. Okay, so now we kind of understand what this h of x given y represent. So that's the information left if you remove the uncertainty of x from the total uncertainty of x and y together. Okay, so I think I might be wrong, okay, but I think the definition of entropy is cooked up so that uncertainty is additive. Right? That's why you have log. That's why you have log. I think that's why you define entropy in this particular way, so that the uncertainty is now additive. Right? It's like in statistical inference, we first define the likelihood, which is the joint density, and in the IID case, it's a product. It's a product, and now you take the log, so the likelihood function becomes a log likelihood function, and the log likelihood function is additive. Once you can add more sample point into your data, and the log likelihood just add an extra term. So it's easier to work with, I guess. Right? Human brains are easier to process additive structure rather than multiplicative structure. Okay, so now here it comes. And now we're going to cover a hugely important quantity, which is called KL divergence, or so-called relative entropy. Let's go. Right? So we're getting somewhere. By the way, we're going to discuss information geometry. I've been keep saying that pretty much in every stream I've been doing right now. It's basically the study of statistics and machine learning algorithm using a differential geometry. And over there, we will discuss a notion called divergence. And the next concept we're defining right now, okay, is going to be an example of divergence. In information theory, this is called a relative entropy. Relative entropy, and in probability and statistics, we call that the KL divergence. So relative entropy. For some reason, the textbook uses the term KL distance, which statisticians and mathematicians desperately avoid because that's not a distance in the metric sense. Okay, in mathematics, distance needs to be symmetric. The KL divergence is not symmetric. Anyway, enough of that, and let's just start with definition. Relative entropy and so-called mutual information. You know, I've been keep hearing these terms, information this, information that, right? If you have done, say, a course on linear model or just model selection in general, you've probably seen something called AIC and BIC. So BIC is the Bayesian information criteria, and AIC, A is the initial of is the first letter of, I don't know, it's a Japanese person's name. I forgot how do you pronounce it. But anyway, this information criteria shows up a lot in statistical inference, in model selection, that sort of business. So basically, the idea of information criteria is you want to penalize complex models. Okay, so in statistics, of course, we want to maximize likelihood. That's the general principle. Of course, that's a popular paradigm. Okay, I'm not saying you always want to do that, but a popular paradigm is to maximize likelihood. But sometimes you want to balance that by considering models that aren't too complicated. That's the Occam's razor principle, right? So the information criteria equals the likelihood minus a penalty term. So for example, AIC, BIC uses different penalty. The overall idea is to punish more complicated models. So information theoretic notions is deeply intertwined with statistics. And here we're seeing a prime example of that. That's the KL divergence, which is defined as follows. Here, the opening paragraph, let's first take a look at. Okay, so that's the opening paragraph. It says as follows. The entropy of a random variable is the measure of uncertainty of a random variable. It is the measure of the amount of information required on the average to describe the random variable. In this section, we introduce two related concepts, relative entropy and mutual information. The relative entropy is a measure of the distance between the two distributions. In statistics, it arises as the expected logarithm of the likelihood ratio. The relative entropy, d of p and q, is the measure of inefficiency in assuming that the distribution is q when the true distribution is p. Okay, this is hugely important. Okay, let's, you know what, the first paragraph is, there's not much essential information, but here, this is important. Here, relative entropy is defined as follows. It's a measure of distance, some sort of distance. It's not quite a distance, as I mentioned, because it's not symmetric. But the idea is there. Okay, how the measure of discrepancy, you can call it that way. So it arises as the expected log of the likelihood ratio. We'll see a formula very soon. So it's the measure of the inefficiency of assuming the distribution is q when the true distribution is p. So that's the relative entropy, d of p and q. Okay, so assuming that the true distribution is p, and if you say use q as your model, of course there's inefficiency there, right? So that's the measure, and you can see why there's asymmetry going on. So if you swap the position of p and q and get d of q and p, the interpretation now changes to assuming that, okay, the first position is always the true distribution. Okay, assuming that q is the true distribution, the inefficiency in assuming p is the model. Okay, so they aren't necessarily the same. In fact, they generally aren't. So there's asymmetry going on here. For example, if we know that the true distribution p of the random variable, we could construct a code with the average description length hp. Okay, yeah. So that was the chapter first section, right? First section we said if you have a distribution and the you can think of the entropy as the average description. As the average description, we have an example earlier. Right? We have a random variable with 4 values a, b, c, d. A, b, c, d, and there's an example of a questioning sequence to determine the value of the random variable. And you can calculate the expected length or the expected number of questions needed. It turns out to be approximately, actually it turns out to be exactly the same as the entropy in that case. But here it is said that in chapter 5, the expected number of binary questions required to determine x is between hx and hx plus 1. So it's pretty close. Anyway, so here, if we take that interpretation and read this sentence, for example, if we know the true distribution p of the random variable, we could construct a code with average description of length hp. If instead we use the code for a description distribution q, then you would have this extra term. Right? The average length would be hp, that's the true length, and this extra term. This extra term. So I suspect this is where we're going. I suspect this is where we're going. So this HP plus DP and Q is HQ. I suppose that's, I suspect that's the case because there's no reason this is not, no? But I don't know, okay? We'll take a look at the definition and verify this. Okay, so here comes the definition. Definition, the relative entropy or Kohlberg, Leibler, Kohlberg-Leibler I never used their full names before. I just used KL divergence. So it's called KL distance. It's perhaps more appropriately called divergence. Okay. In statistics, we almost always say KL divergence. Between two probability mass functions defined as follows. Between Px and Qx, PMFs P of x and Q of x is defined as follows. Is defined as d of P double dash Q defined as the sum of x in big X, P of x of log P of x over Q of x. Right? So recast this as an expectation. This would be the expected value of, assuming P is a true distribution, okay? And there would be log of P of big X over Q of big X. Right, so in the middle, the function taking expectation is exactly log likelihood ratio, log LRT. Right. Likelihood ratio, of course, is hugely important in statistics. So, for example, likelihood ratio test. Okay, and in the definition, we also use the convention. When you have 0 times log of 0 over 0 is treated as 0. Um, 0 times log of 0 over q is taken as 0. Okay, and p, so here we're assuming if q is non-zero. Okay, so if q is non-zero, then you take this as 0. This is justified earlier. So p times log of p over 0 is taken as infinity. In fact, this is not even a non-determinant form because, well, you get log of infinity here. But hold on a second. Yeah, that's correct. That's correct. So that's correct. Yeah. So that's the definition. That's the definition. So it just immediately raises the question, though. So does the identity hold? Does the suspected identity hold? Remember, what is HP? All right. What is HP? HP is the sum of over x, P of x, log of P of x. Sorry, guys. a minus sign. Don't forget the minus sign. Okay? And here now we calculate what is h of p plus d of p double dash q. What's that? We have the definition. So this is minus the sum over x, p of x log of p of x. I don't know what's wrong with me today. Summing over x, p of x. Is that right? This doesn't simplify, no? You see, p is on top in the ratio. So the log doesn't even simplify. This is not h of q. So I'm a little bit confused here. So d, the relative entropy is not the difference in entropy. That's for sure. Okay, so I don't know why this interpretation is given. Okay, it's my cat. So, right, if you know the true distribution, which is p, you use hp to describe, you use a code with average length hp to describe random variable. And assuming that p is still, the true distribution, but you're using the code. You're using, let's say, a code for distribution Q. Then you have this extra term, but this is not HQ. So let me erase that. So HQ would be, okay, HQ would be the average length required, the average length of the code required to describe a random variable with true distribution Q. Here you see we're talking about something else. The true distribution is still assumed to be P, but instead we essentially made a mistake, right? We're using the wrong code. If we use the wrong code, then the length increases by this much. And by the way, actually, is this always positive? Actually, we don't even know, right? Let's check out the property of this new notion, KL divergence. Okay, so that's the KL divergence once again. This is a formula that will show up a lot. This is a formula that will show up a lot. Okay, so let's see what else we can say about it. So it says, because of the last convention, this shows that if there is x in big X such that p of x is non-negative, is non-zero, and q of x is 0. Okay, then d would be infinite. Let's think about what this means. Okay, let's try to, because right now we desperately need intuition of what this represents. Right, brute force calculation is important. Right? We need to be able to calculate things, but still, it's important to understand what these things measure. So, imagine there is a value. Imagine there's a value that is attainable by x. Right? Attainable by the true, attainable from a attainable. Sorry, my goodness, has a non-zero probability to occur in the distribution P, but has a 0 probability to occur in Q. Then the divergence will be infinite. So that is to say, the two distributions don't even have the same support. If two distributions don't have the same support, we consider the distance to be infinite. Right? That's the interpretation here. Okay, I don't know what's the advantage of doing that, but let's just keep that in mind. By this convention, we are forcing the distance, the KL divergence to be infinite when two distributions have different support. If P and Q have different support, then the KL divergence is infinite. Okay, so let's continue reading the text. So here you have a bunch of commentary. Let's read that before we proceed with the new definition. Here it says, we will soon show that the relative entropy is always non-negative. Okay, great. And is zero if and only if P and Q equals zero. So it kind of behaves like a distance, right? That's cool. However, it is not a true distance between distributions since it is not symmetric, as I was saying. And does not satisfy, actually it does not satisfy the triangle inequality either. Oh, I thought it does. I thought it does. I think I made a stupid comment earlier in the stream. I was doing the tensor stream because there was a little bit of a digression on KL divergence, but it turns out that does not satisfy triangle inequality either. Okay. Nevertheless, it is often useful to think of the relative entropy as a distance. Okay, you think of it as a distance. And we now introduce mutual information, which is a measure of the amount of information that one random variable contains about another random variable. Mutual information. So it is the reduction of the uncertainty of one random variable due to the knowledge of another. Okay. Okay, so we will prove the properties later. Okay, we'll prove the properties of KL divergence later, but let's now just define the mutual information. Once again, there are a few equivalent definitions. I guess just like in the conditional entropy, it's useful to keep in mind all these definitions. So sometimes one is perhaps more is easier to work with than the other. For example, when we prove the chain rule here, when we prove the chain rule, it is clear that if you use the expectation definition, then the proof is just one line. So user says, so it's extra sensitive to tail mismatch. Yeah. I think that's the answer here. That's the answer here. So let's say if you have two distributions, like so, one like this, one like this. So they don't even have the same support, then the KL divergence is immediately infinite. Okay, but if you have like a two Gaussian distribution, then such issue does not occur. Right? Yeah, so it's extra sensitive to tail mismatch. Is a good way to put it. I like it a lot. All right. Okay, so now let's define mutual information. So once again, you have x and y discrete with the probability mass function p of x and y. Okay, and x has px, y has py. Actually, I don't really like this because it feels like the same function with different variables being substituted, right? So this feels awful. But this is how they do it in the textbook. I mean, in statistics, you would write px of x, py of y to emphasize these are different functions. And the joint distribution would be written as pxy of x and y as well. Perhaps this issue never really occurs in information theory, I don't know. But this looks a bit sus. from a statistician point of view. Okay, so far I guess we understand what it says. Just be mindful of its interpretation. These aren't the same functions. All right. So anyway, so this is a setup. Mutual information is defined as follows. Mutual information, I x semicolon y, okay, it says is the relative entropy between, is the relative entropy between, is the relative entropy between, so basically that's the KL divergence, between what? Between the joint distribution and the product distribution. So this has a nice interpretation. Of course, the product distribution is the distribution if we assume x and y are independent. So mutual information is defined sort of as a distance between the true joint distribution and the distribution in the IID case, also in the independent case, not necessarily IID, but independent. So you have the sum over x and the sum over y. Okay, the true distribution is, of course, the joint. And then, okay, by the definition of the relative entropy, you put the true distribution on top of the ratio inside the log. And at the bottom, you have P of x times P of y. So here, this is the joint distribution as if x and y were independent. Of course, in the case of independence, you know you cannot derive information from y using x. Right? So this is like the zero information case, zero mutual information case. X contains zero information about y, y contains zero information about x. Right? So now, if you measure the relative distance between the two, the relative entropy between the two, you know how far the joint distribution is from independence. That's the idea. So here, this is the joint distribution of x and y as if x and y are independent, using the notation of independence from statistics. Right, so that's the definition of mutual information. Now, of course, now it's just a matter of rewriting this in a different form. You can write it as the expected value of big log, sorry, not big log, just log of P big X y over P big X P big Y, okay? Okay, there's that. And it is also, as we said, the relative entropy or the KL divergence, so you get D, sometimes you write it DKL at the bottom, okay? Because in statistics, there's multiple versions of divergence, right? In particular, in information geometry, you can argue that information geometry is the study of divergence. Now, in information geometry, there are many different versions of divergence other than KL, even though KL is perhaps the most popular. So you have the divergence between the true joint and the hypothesized, okay, the independent joint, P of x times P of y. These are all equivalent definitions. Okay, so far, I just want to remark that so far we've been only working with discrete distribution. Okay, later on in the book, in particular, it says in chapter 8, it will be generalized to continuous random variables and general random variables. So general random variables that may not be discrete or continuous. Okay. So, but here we're just using discrete random variables to drive the intuition. Let's go. So before proving the theorems, let's first look at example. Example, this is 2.3.1. Okay, so that's suppose you have scripted x, the values of x being 0 and 1, and consider two distributions q and p and q on x. So you have two Bernoulli distribution. Okay, so this is p. X, take value of 0 and 1, p of x, p of 1 is r, p of 0 is 1 minus r. And then you have q. Second distribution still takes the value 0 and 1. Q of x takes value 1 minus s and s. There you go. So the two distribution. And let's calculate the KL divergence. And we can clearly see they aren't symmetric. All right. So what is d of p and q? D of p and q. So assuming p is the true distribution. Okay, so let's write that. So first of all, here, by definition, this is the sum over x, which are just two terms, from 0 to 1, okay? And p of x log of p of x over q of x. Okay, and what's the other version? Oh, sorry, what's the opposite? So you have d of q and p, assuming q is the true distribution. The divergence is sum from 0 to 1, q of x times the log of q of x over p of x. There you go. All right, so it's really easy to write down the sum. So when in the first case x equals 0, p of 0 is 1 minus r, okay, times the log of 1 minus r over 1 minus s, and then plus r log of r over s. And here downstairs you get q is the true distribution is 1 minus s, log of what? 1 over s over 1 over r, plus s times the log of s over r. Okay. Okay. In particular, you notice they are on the same in general. Okay. So that's the two definitions: mutual information and KL divergence. Hopefully, the intuition is now a little bit more transparent. Okay. Let's box that. Mutual information. All right. So we're happy with that. Sort of. At least there's no biting contradiction in our face. So that's kind of nice. Okay, stop lagging. One note. Okay. There might be some AI feature running in the background that slows down the program. I don't know. But anyway, let's continue. Next section, 2.4. Okay, so just to keep in mind of our progress, so the exercise all left at the end. Okay, so we were here. We are here right now. We are here right now. So I know sufficient statistics depend on data processing inequality. So we might not be able to get to that point, but I will stop at 12. Okay, so there's 2 hours and 20 minutes to go. So there you go. Let's take a look at the next notion. Next section. The next section is called relationship between entropy and mutual information. between entropy and mutual information. Okay, so you see, I was suspecting there's some sort of relation between H and D, right? So I postulated that HP plus D of P and Q equals HQ, but it was quickly disproven. So this is not the H of Q. Okay, so let me put that in green color. So typically speaking, blue is the main color, green is like exploration, and red is highlight. And the notes are uploaded. Okay, I'm trying to upload all my notes. But I don't promise a timeline. Okay, so if you want specific notes for a particular live stream, please let me know. Okay, chat has been real quiet, but there's still a lot of people watching, 14 people. So I don't know if everyone is just happy about the speed I'm going through, or I don't know. Like, yeah, feel free to leave your comment, right? So yeah, this is like as I said, this is like a community-driven learning experience, a seminar. This is by no means a lecture, because I frequently confess I don't understand this and that, right? So feel free to pitch in your thoughts. Thank you so much. Anyway, let's continue. So here, relationship between entropy and mutual information. So we're going to rewrite the definition of mutual information as follows. So usually it has to do some funny business with the property of log. So I of x semicolon y is the double sum over x and y, p of x and y, right? The log of p of x and y over the product distribution. Okay, there you go. And then you do what? You use the definition of conditional distribution. So the sum over x and y, p of x and y. Here we consider rewriting p of x and y over py as the conditional distribution of x given y. So what we did here is this. So we combine these two and put that as a conditional. Okay, this is what we did. All right, and then you use the property of log to convert this into, hold on a second. There's no minus sign, huh? You see in the divergence, chaos divergence as well as mutual information, there's no minus sign. Sure. Okay, so and now let's use the property of log and break this into two terms. So this minus sum over x and y, p of x and y, log of p of x. There you go. And then plus the sum over x and y, p of x and y, times the log of the conditional, right? P of x given y. There you go. So we instantly recognize there's few familiar faces going on. So first of all, if you sum over y in the first one, then log of p of x, that's not related to y. So you just need to sum over p of x and y over y. And that gives you the marginal distribution of x. So this is just the sum over x, p of x, times the log of p of x. So this is very promising, because this is, here, the first term is just the entropy in x. Okay? And the second one, let's rewrite this as minus the sum of x and y, p of x and y, the log of the conditional. Remember, the second term is what? The second term is the conditional entropy. So therefore we have the following identity, which is I x semicolon y is h of x minus the conditional information, conditional, not information, conditional entropy. So what's the takeaway here? The takeaway is, okay, therefore let's write, therefore I x y equals this, and we're going to box that. So the idea is the mutual information, which we defined in the previous section, is the reduction in the uncertainty of x due to the knowledge of x. Let's compare this. Okay, compare this with the chain rule. So compare this with the chain rule. The chain rule says what? Here, actually, in the chain rule, well, the chain rule says the uncertainty in the joint distribution is the uncertainty in x plus the uncertainty in the conditional, right? And then now, as I mentioned earlier, you can cook up this relation, right? Because h of x and y can be written in two ways: h of x plus h of y given x, and h of y plus h of x given y. And then just rearrange, you get this. But the left-hand side now has a meaning. The left-hand side is the mutual information, isn't it? The left-hand side is now the mutual information. Hold on a second. This seems rather profound, huh? Look, we just showed that I, x and y is h of x minus h of x given y. This is I, x given y, so that's the left-hand side. And, well, by the symmetry, and also by symmetry, we have actually, you know what? Hold on a second. This is, I'm saying is if you swap, not by symmetry, just by swapping the position of y and x. In this identity, if you swap the position of y and x, you get what? I of y and x is h of y minus h of y given x. And actually, it should be symmetric. Notice in the definition of I, x and y is symmetric. X and y is if you swap the place of x and y, what does that mean? Well, here in the summation, the first factor is still the joint distribution of x and y. That hasn't changed. Which means in the log, upstairs hasn't changed, and the bottom, you just swap the position of the product, so nothing has changed. So they should be the same. So it should be the same. So now, I mean, it's not terribly profound, but it's still, I guess, this is not just a random rearrangement. Both sides actually has meaning now. As promised, this will be useful, and indeed, both sides now equal to the mutual information. So the terminology called mutual information seems rather appropriate, right? If something is mutual, then it should be symmetric, right? It should be symmetric. So this is the formula for the mutual information. You can calculate mutual information from entropy and not relative entropy, but conditional entropy. So yeah, very useful stuff. Okay, so that's the relationship between mutual entropy, mutual information. There's no such thing as mutual entropy. Mutual information and entropies. Okay, so that's a nice result. So basically, let's summarize the meaning. Okay, the meaning of this. Let's call this 1 and call this 2. 2 is also can be expressed as x semicolon y equals y semicolon x. There you go. So interpretation. One says, what is I? I x semicolon y is the reduction in the uncertainty of x due to the knowledge of y. Okay, so that's a nice way. Now this is good. What do you mean this is good? Is there did I raise a problem? Okay, so 2 says, because of the symmetry, it says x says as much about y as y says about x. Says x says as much about y as much about y as y says about x. So this is useful. This is useful. So now let's combine this relation with the chain rule. Right. So by the chain rule, let's recall the chain rule we just derived earlier. You have h of x and y. That's the joint. Sorry, not the joint entropy. Yeah, joint entropy can be written as h of x minus plus h of y y given x. Yeah. Okay. And you can isolate the conditional entropy and you get the mutual information I of x and y equals h of x minus, hold on a second, yeah, plus h of y minus h of x and y. Yeah, so this further shows, actually, you know what, let me write it as fully, h of y plus h of x given y. So isolate h of x given y. H of x given y is h of x and y minus hy. Substitute that into 1, you get this. So this is an important formula. So from here, it is crystal clear that I is symmetric. It is crystal clear that I is symmetric. So that's an important important formula. And also, if we have, say, y and x are the same, what do you get? First of all, what is the joint entropy when x and y are the same? Go back. If x and y are the same, then the joint distribution is the same as the marginal distribution, no? If let's say there's a deterministic relation between y and x, y is equal to x in all circumstances. Y and x are the same random variable. Then the joint density is the same as the marginal density, or the marginal PMF. So basically, this is just, and also you can see it from the what? From the chain rule. From the chain rule, if you know x and y equals x, so there's no uncertainty anymore. Right? If y and x are the same, special case, perhaps it's worth writing this here. If y and x are literally equal, if y is a deterministic function, y is literally equal to x, then what? Then, well, here in this expression, it will just be 0. So I'm trying to say is here it's clearly h of x given x is 0. Okay, h of x given x is 0, and therefore the mutual information between x and itself is just the information. It's just the entropy in x. Okay, and I of x and x is just hx. Information theory, what is treat. Right. I know it's still very new. I'm still very new to the subject, but I like it. I like it a lot. Okay. So entropy is sometimes called the self-information. So-called self-information. Another name for entropy. Okay. Collecting the results together, we have the following results. Okay, collection, cheat sheet. This is theorem 2.4.1. So together you have this relation. Okay, the mutual information is hx minus the conditional entropy h of x given y. Also, this is hy minus the conditional entropy y given x. Okay, and I hate to say, the third formula, this one, looks like the exclusion-inclusion principle in probability, right? I don't know about you, but this one reminds me of probability of A intersect B. Actually, union. A union B, or A or B. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. I don't know if there's some sort of deep connection going on, but this is what reminds me of. This is the so-called inclusion-exclusion principle. Okay, so anyway, h of x plus h of y minus joint information. All right, let's keep going. And then you have symmetry. Okay, and finally, so-called self-information, which equals the entropy in x. Okay, so this is the collection of formulas. Anyway, so here, there's a diagram. It says the relationship, there you go, let me just draw the diagram. This is here you have this circle in a Venn diagram. Of course, this doesn't mean set. Okay, this doesn't mean set. Yeah, because remember, I was just talking about the exclusion-inclusion principle in a second. Right? If you think of this as set, this is set A, this is set B, event A, event B, then the total area covered by the two events would be the probability of A or B. So by that analogy, we interpret the full region, okay, the region covered by both circles or whatever, and call that h of x and y. So that's the total or the joint information. All right, so that's the joint information, and in the middle, by the inclusion-exclusion principle, in the middle you have the mutual information. Kind of works like intersection, right? It kind of works like intersection. Anyway, and the individual circles are the uncertainty in x and uncertainty in y. Okay, and of course, the different set, quote unquote different set, would be the conditional. It plays the role of the conditional information. So hx minus h of x given y gives the mutual information, and hy minus the conditional information, h of y given x, gives the mutual information as well. Right. So that's the diagram. So it's a quick way to memorize all these formulas, which I think is pretty cool. So you know what? Let me reorganize this as such. I just place the formula and the picture side by side. Okay, beautiful, huh? Okay. Anyway, so now let's take a look at the example earlier. Well, what's the example earlier? So in our example earlier, we can put all those numbers together. Here, in this example, on the side, let's just put all the numbers together. Here, this is hx. Hx is what? It's 1.7 bit. Okay, I'll not write bit, but basically that's hold on. Reuse the circle. So this is hy. Hy is what? Hy is 2. Right? And the mutual information, we don't know yet. We didn't calculate that, but the total or the joint information is actually, this is confusing because joint, you think about the intersection. The word joint strongly suggests intersection, but here the joint information represents the whole. It's quote unquote the union. Okay. The h of xy is 3.375. Okay, and in the middle, you got the mutual information I semicolon y. We didn't calculate that, but it's not hard to figure that out because here we calculate the conditional entropy. H of x given y. This h of x given y is this part. H of x given y is 1.375. And indeed, 1.375, that's this difference set. That's the area of this difference set, quote unquote. And then plus 2 gives you 3.375. The chain rule, which is we just verified. Okay, and this part is h of y given x. Okay, so from the picture, we can immediately calculate the mutual information is 1.75 minus 1.375, so it's 0.375. Right? And from that, we can deduce the other conditional information, h of y given x is 2 minus 0.375, which is 1.625. Here, that's the answer we wish to. We asked you guys to verify independently. Okay, so now you have this nice little diagram. Okay, next section. 2.5. So see, I like this book a lot because each section is very short and digestible. You can probably finish, maximum, a section within an hour. This is very digestible. Hopefully the rest of the book also have this sort of arrangement. This book is highly cited for a particular reason, I guess. This is very user-friendly. Okay, and now let's consider the joint entropy of more than two random variables. Okay, 2.5 is called chain rules. More chain rules. Chain rules for entropy, mutual information, okay, and relative entropy. So these are the crucial concepts we've been studying so far, right? So it's all here. Entropy, perhaps also conditional entropy. Entropy, conditional entropy, mutual information, relative entropy. Actually, relative entropy comes first, and mutual information is defined in terms of relative entropy or the KL divergence. Anyway, let's go. So here it says the following theorem. 2.5.1 says a chain rule for entropy. Still, I don't know why this is called the chain rule. From calculus, the chain rule familiar in calculus has a nice chain diagram, right? But I don't know why it's called a chain rule. Anyway, so if you have x1, x2, x all the way to xn, these are random variables. It has the joint distribution. Once again, we assume discrete distribution. Okay, p of x1, x2 all the way to xn, n-dimensional joint distribution. Then you have the following. So h of x1, x2 all the way to xn, that's the joint entropy of all of those random variables. Is what? Is the sum of h, okay, the sum of h of xi given xi minus 1 all the way to in. So, interesting. Let's write down the formula without the summation notation. Okay, see what does that mean? When I equals 1, that's just h of xi given h of x1 given x1, which is just 0. Hold on a second. I minus 1. Perhaps it's better to rewrite this formula. Actually, this is the original formula in the text, but I don't like it. I don't like it because when I equals 1, on the right you get apparently an x0, which is undefined. So let's just going to change the formula a little bit, okay? So it means the following. It means the following. So here you have x1, h of x1 plus the sum I from 2 to n. This is what it means. Okay, this is what it means. So, all right. So, okay. For example, that is to say, for n equals 2. I mean, for n equals 1, the statement is meaningless or it's trivial. So n equals 2, 3, and so on. So you have two variables, that's h of x1, x2 is h of x1 plus h of x x2 given x1. Yeah. Right, that's just the chain rule. And then h of x1, x2, x3 is what? Is h of x1 plus h of x2, x3, right? So here we're just using the two-term chain rule. And now I guess this is the namesake of the chain rule. You just like keep breaking down stuff. So here, you have h of x. Hold on, this is h of x2 h of x2 given x1 plus h of x3 given x2, x1. Here just repeatedly apply the two variable expansion rule. This is nothing but repeated application of the two variable expansion rule. I think I'm bothered by it being using called the chain rule and not related to calculus. I know. I have the same feeling. Actually, you know what? There's another chain rule in probability. I'll show that in a second. This repeat application of the two variable expansion or entropies. Okay, so I think the analogy comes from the following. Okay, so analogy in probability, analogy to probability theory. This is what's going on. So let's say you have two events, probability of A and B. So you want the probability of A and B. What's the probability of A and B? Well, that's probability of A. Sorry, probability of A times the probability of B times probability of A. Right? And then consider three events, A, B, C. What's that? Well, that's the probability of A times the probability of BC given A. Which is what? Which is, you can keep expanding this. So you just push things into the condition. Oh, hi, Vernon. Thank you so much for joining the stream. Glad to see you again. So, well, what's that? Well, that's PB given A times P C given AB, BA. And you can just imagine how it generalizes to arbitrary finite sequence. And by the way, here AB means the joint event. I think this is the analogy. I think this is called the chain rule improbability. So it has nothing to do with the chain rule in calculus. Does that make you feel better, arcane compiler? Yeah, this is the chain rule improbability. Yeah, so maybe this is perhaps a little bit nicer, okay? And now let's define the conditional mutual information. Definition. I think the proof is now clear, no? I think the proof is now clear. So, I mean, the formal proof would use the induction argument. You check the base case, and then you use the inductive argument. Okay, and that's not essential here. Okay, so now let's define the next notion called the conditional mutual information. So conditional mutual information of random variable x and y given z. X and y given z. Okay, so this is defined as, this is a definition. Okay, it's not a theorem that you proved. So this is a definition of the conditional mutual information of x and y. So write x semicolon y given z. Okay, this is the quantity, and we define that as h. Okay, as h of x given z minus h of x given y and z. All right, so hopefully everything is clear, right? So why do we do that? Well, it's obviously inspired by this identity here. So it's obviously inspired by this one. Okay, because this is, I'm not using a university lecture hall. I don't have 4 blackboards at once. Okay, so I need to go back and forth quite frequently. I apologize for that. So that's the inspiration. So this is the unconditional mutual information. Remember, this is unconditional mutual information, and now you're just pushing. It's like, okay, it's like you have an extra z given z at the end. You just add extra given z to every term. Right, so that's the motivation for defining conditional mutual information this way. It seems like an obvious candidate. Okay, and remember, what is the meaning of mutual information? Earlier, what is the meaning of mutual information? Mutual information is a KL divergence. Is a KL divergence the distance between two distributions, in the sense that if you're assuming one distribution is true, the quote-unquote inefficiency of treating another distribution as the model, right? And the inefficiency is measured by the log likelihood. That's the expected log likelihood, right? So here, let's write that down as the definition. As the definition. So I guess you have to verify that, no? Here, I mean, in the definition, it's simply right. Okay, this is equal to E pxyz of the likelihood ratio of px1y given z. And I think we need to prove this though. The first line is a definition, the second line should be a theorem. Okay, I think you have to show this, no? So the idea is, thanks for the booking for chapter 16.2 looks interesting. Okay, I'm still in chapter 2. Okay, so this book is, by the way, as I mentioned, highly regarded as the Bible. It's widely regarded as the Bible of information theory. So I think this needs to be proved. This one is a definition. However, in the textbook, though, it is combined into one. Or unless from the first line to the second line is very obvious, which I'm not quite sure. So why don't we show that? Okay, why don't we show that this is a theorem? I think this is a theorem. So now let's prove it. Okay, let's prove this is equal to this. So let's do that. So the expected value with respect to the joint distribution xyz of the function log of pxy given z, oh sorry, big Y, big X, big Y. Yeah, it looks biblical. It's very comprehensive, right? And surprisingly approachable from a newcomer to the subject. It looks very promising. Feels like it's something that you can actually read and learn from it rather than decoding it. Okay. It's not baby Rudin, this text. It's not like to read one book you need like 10 other books to help you out. Like, all right. Okay. So let's expand this. How? So this is the summation over x, y, and z. P of x, y, and z times the log of p, okay, of x and y given little z divided by this. Okay, so there's that. P of x given little z. Just wait for Papa Rudin, much worse. I know, right? And Papa Rudin is also pretty non-standard. I mean, I never seriously studied it, so I can't comment nothing. Because my reading experience when it comes to measure theory and whatnot is very limited. My grad school uses Rudin, not Rudin actually, Folland, which is very painful, and professor's notes. Okay, so recently I started going over Sheldon Axler's measure theory. I couldn't when I was still in university because the book was not even published at that point. And I didn't even bother checking Papa Rudin because Folland is already very painful. Okay. Anyway, so there's that. Okay, so I don't know what else we can do here. I don't know what else we can do here. So perhaps it's a good idea to say, actually, you know what? Let's use an identity. By the chain rule in probability, right? We wanted something. Yeah, we used that trickery earlier. So here, this is what I'm about to do. So I'm going to use the definition of conditional probability or use the chain rule. Okay, so here, this is P of x given yz. This is P of x given y and z. and P of X given Z. So this is pretty immediate. All right. So from this point, the definition and the theorem should be in the theorem part. Okay, the second equality should be clear. Okay, and then you just use the property of log. You get minus sum of x, y, z, p x, y, z times the log of x given z, and plus the sum of x, y, z, the p x, y, z, the log of x given, p of x given y, z. There you go. So, I mean, here you can see y is independent of the log term. So you just sum over y in the function f of x, y, z. So this way you just get the double sum of x and z, p of x and z, log of x given z. Well, still 17 people watching. That's insane. Okay, thank you guys so much for sticking around. I don't know why, but this is very baffling to me. Okay, initially I decided to stream my own study progress, but I didn't expect people would watch. This is very long, and you have all the things in the world to do. You can watch. Well, I mean, World Cup is over. You have no World Cup to watch. Perhaps that's the reason you're watching me. But anyway, so I'm just saying that there's so many other fun things to do, right? But you guys choose to stick around and see some random guy on the internet do math. But this is awesome. Okay. Anyway, so here this is proved. Okay. So indeed this is the same. All right. So we're done here. Conditional mutual information makes sense. And now we have the chain rule for information. We also have the chain rule for information. So actually, yeah, let's write the statement down. Theorem 2.5.2. There you go. Theorem 2.5.2 says the chain rule for information. Okay. I'm a little bit disturbed by the lack of example going on in the text. Perhaps they're all left as exercises. But we're here to see some random math. Okay, great. Great, yeah. So, okay, so you have the chain rule for information, which reads as follows. So I think once again, I dislike the notation. So in the text, it says the sum, I from 1 to n. Big I, xi, for some reason there's a y singled out at the end. I don't know why. But xi, semicolon y given xi minus 1, xi minus 2, all the way to x1. So perhaps, okay, just perhaps, it didn't say explicitly in the text, but we've seen this twice already. So perhaps let's just respect the standard notation. That's the Bible of information theory after all. So we know what it means, but basically I'm saying is when I equals 1, it is treated as the unconditional entropy. There's no way you don't do this performative. How do you context switch between a different math domain in a week? What do you mean by performatively? I'm not like I seriously I never took this before formally. Okay, just based on the question I asked, does this sound like I'm like doing a persona? I don't know about you. Okay, these are let's say if I I mean, I don't know how to put this because I have no way to prove this, because if there's nobody watching, I'm just going to do this process on my own, save the talking. But it's going to be pretty much the same speed. Okay. Here, anyway, I'll stop defending myself. The convention is as follows. Um, the convention is as follows. So you have when I is equal 1, when I is equal 1, this is just treated as the unconditional entropy. Because I was bothered with, oh, when I equals 1, then you get x0, which is not defined, right? So this is the convention. So this way, the first term is now clear. Okay, and I think we use the same convention here. So in the convention, when you have I equals 1, then there's just the unconditional mutual information. Convention. So, all right. So when I equals 1, you get I of x1 y. That's it. That's it. Right. Because as I mentioned, the reason I started doing this one, I did this one. And there's no plan to make this regular. Okay, I'm just saying there's no plan to make information series a regular feature on the channel. I have no plan for that because there's a lot of competing interests going on. The reason I did this is because there was a viewer request during the mathematical finance stream, and they wanted to see some information series. Like, okay, why not? Right? I didn't expect much because I never had any experience. I don't know whether I was able to do it, or is the subject even doable, or something else. I didn't know. And later on, in my mathematical statistics stream, Leo told me, from Leo lecture, told me that sufficient statistic apparently has an information theoretical viewpoint, which I completely could not comprehend what he was saying in chat at the time. And now we're working towards it. So yeah, and yeah, this you can see here in the content. 2.9 is about sufficient statistic. And just by briefly looking through the content, it requires the knowledge of data, so-called data processing inequality, which I'm not sure we will have time to get to. We have an hour and 20 minutes left. We'll go as far as we can. Okay, but the thing is, I'm interested in the subject, I mean information theory, from the viewpoint of statistical inference, because that was my background. Okay, that was my background. And there are so many things in statistical inference that are inspired by information theory, and it has some sort of informational theoretic argument to it, because I never took it and I wanted to see the subject for myself. Okay, I don't know what else can I explain. But basically, yeah, that's coming back to the content. Here you have the chain rule for information. Okay. The chain rule for information says the following. And let's just write down a few terms to see what it is about. So for example, I of x1, if you just have two terms, I of x1 and y, according to the definition, so n is 1, huh? Oh, that's trivial. There's nothing going on. See, when I equals 1, there's nothing going on. It's just a trivial identity. Both sides are the same. So move on. If you have two terms, two x's, okay, you have x1, x2. x1 and x2. Here you have the sum, which is when I equals 1, as I said, it's just I of x1, y. Right, and I equals 2, you get, hold on, that's I of x2 and y, and then you get just x1. This is what it says. right? That's what it says. All right. So if you have three terms, let's say x, ix1, ix2, ix3, no, sorry, ix1, x2, x3, column y. I think the idea is, okay, I think the idea is you're considering the first n random variables as a random vector. So you're considering the mutual information really between the x's and y. So these are the two parties, okay? Something mutual involves two parties, right? Mutual agreement, whatnot. So the two parties involved are x1, x2 all the way to xn, and y. Okay, and now say expand according to the theorem, you would get I of x1, yeah, I equals 1 is just I x1 y, and then plus I of x2 y given, well, this is x2, x1, yeah, x1, and then finally I of x3, semicolon y given x2, x1. There you go. Three terms. Okay, so to prove this, what do we do? To prove this, let's just use the fundamental identity for mutual information. So I of x1 all the way to xn, semicolon y, is the joined information. Sorry, just the information in x1 to xn. Remember the Venn diagram here, the Venn diagram. These are the two parties, right? This is hy, this is h of x1 all the way to xn. So you're interested in the middle. So I'm saying is, you start from the left circle, h of x1 all the way to xn, minus the conditional entropy, that is x1 all the way to xn given y. And then you just use the chain rule for the entropy, then we'll be done. So use the chain rule for the entropy, you get the sum, right? Use the chain rule for the entropy, that will be the theorem 2.5.1 theorem. Okay, sum of I from 1 to n, so h of xi given xi minus 1 all the way to x1. Okay, yeah, this is the chain rule, exactly, the beloved chain rule. And that's another, yeah, so that's the chain rule holds for conditional entropy as well. You just keep given y at the end. So h of xi given xi minus 1 all the way to x1 y. Okay, and then you combine the two sum. What do you get? Well, it's just the sum that you wanted, right? I from 1 to n, mutual information, xi with y given xi minus 1 all the way to x1 as you wanted. QED. Okay, so there's that. Now, the proof is rather short. Chain rule for information. Actually, you know what? Let me box the formula because it's easy to miss the formula. So anyway, so this is the chain rule for entropy. Here you have the definition of conditional mutual information. And here you have the chain rule for information, for mutual information. Actually, it's for information. I mean, it is a mutual information, no? So far, we've only encountered mutual information, so yeah, this is a mutual information. It's just now the mutual information can be taken between a finite sequence and something else. Yeah. All right. So that's cool. So also we will define something else. That's called the okay. This part of the text seems to lack example. Perhaps they're all hidden in exercises. Who knows? Okay. So let's just keep pushing. Definition. The definition. The next thing we want to define is conditional relative entropy. Conditional relative entropy. So we're given PMFs, P of x, y, and Q of x and y. Nice? So the conditional relative entropy, remember relative entropy is just a KL divergence. Conditional. Okay. Let's first describe this verbally. I want a bigger space. Conditional relative entropy is a notation d of p of y given x, okay, and q of y given x. So how is that defined? So let's first think about it for a moment, right? So what's the natural definition here? Remember, what's the definition of what's the definition of relative entropy? Well, the KL divergence. We mentioned that earlier. So if let's say this is a P, this is a Q, okay? We're assuming P is a true distribution, and we're measuring the expected log likelihood ratio of P over Q. So P is true model, assuming P is a true model. And you take Q as the fitted model, whatever, your chosen model. Right? That's just a plain vanilla relative entropy, KL divergence. But now you have this conditional thing going on, right? So I suspect you would probably first you consider fixing x. So when you fix x, the two conditional distributions are fixed, and then you calculate the KL divergence as usual, and you weight that, and you weight that function of x based on the distribution of x itself. So that's the intuition. Let's see if that's correct. Okay. So the verbal description as given in the text is the conditional relative entropy is the average of the relative entropies between conditional probability mass function. Exactly what I just described. And the average is over the PMF PX. So there you go. So let's first write down the formula. Actually, we just described that verbally. Let's first write down the formula. So you have d of p y given x compared with q of y given x. Right? And you want to sum over x px. So that's the expected value relative to x. All right? So there you go. And then you have, what do we say? You're assuming p y given x as the true distribution. So p of y given x stays here, and then you take the log likelihood ratio. So p of y given x over q of y given x. Right? So this way we don't have to mechanically memorize all these definitions, because this right. So if you understand what this formula is doing, then it's pretty straightforward. So first you fix x and you calculate the usual KL divergence as usual. But in that case, you will have a function of x. And now you calculate the expected value of that function of x. So you're done. So that's the idea. Hold on a second. All right. So yeah, there's that. And of course, you can rewrite this as the sum over x and y. Px times the conditional gives you the joint. And now you can write that as expectation. Right? So this is just the expected value, assuming p of x and y is the true distribution of the function log, right, the log likelihood ratio between the two conditional densities. All right, so there you go. Conditional relative entropy, conditional KL divergence. Okay, and I believe there is a chain rule coming up for that as well. Lots of formulas, of course, these takes practice of exercises to master. It is said in the text the notation for conditional relative entropy is not explicit, since it omits the mention of the distribution P of x of the conditioning random variable. However, it is normally understood in the text. Well, it feels to me that it is mentioned, right? Given x, it is mentioned. That's odd. All right. At least we understood the idea, the formulas, and the interpretation. So next, the chain rule for the relative entropy. Oh wow. It says, wow, that's pretty cool. The chain rule for the relative entropy is used in section 4.4 to prove a version of the second law of thermodynamics. Okay. Wow. Here, this is a theorem. 2.3.5 chain rule for relative entropy. Okay, let's just remark that this is used in 4.4 to prove the second law, prove a version of the second law. Okay, physicists in chat, please help me out here. I never know that second law can be proved. I saw second law was empirical. Perhaps in statistical mechanics you can prove the second law. I thought like thermodynamics is I mean it like if that's the case, then can you prove energy conservation, the first law in thermodynamics? Sorry, in statistical mechanics, isn't that just the axiom? Okay, I'm very intrigued here. Right? So as far as I know, the first law of thermodynamics is energy conservation. Energy cannot be created or destroyed. You don't prove that, you just work with it. Right? Or actually, or you can treat it this way. Our quantities in physics are defined in such a way, namely energies are defined in such a way, energy, work, heat, all those stuff were defined in such a way that they remain an equation. So it is a tautology. So energy conservation seems to me a tautology. Why is the kinetic energy half mv squared in classical mechanics? You define that so that you can have a nice identity called the work energy theorem. Right? So work is the difference in energy. So and then you consider, oh, when the work is done by conservative force, boom, you have mechanical energy conservation. So the whole thing is a motivated definition so that you can have an equation. So the formulas for the energies are defined in this way that the equation holds. And of course, when classical mechanics breaks down, you don't call kinetic energy half mv squared anymore. Instead, you called it the k is the moving mass c squared minus m naught c squared. So this way the energy still remains conserved. It is impossible to prove or disprove the first law precisely because how energies are defined, right? And how do you define? How do you, let's say, prove the second law? How do you prove the I have no clue. This is very intriguing. I thought second law was empirical. I thought the second law is purely empirical, and you just work from it. Perhaps, I don't know, in statistical mechanics, you can use more fundamental principles to prove the second law. Yeah, microstates and their property. Perhaps that's how the second law is so-called quote unquote derived from or proved or whatnot. Okay, so it's when something is proved. Okay, it always means if such and such and such, then such and such and such. The verification of the implication is done. That's what we mean by a proof. Right. So in thermodynamics, in classical thermodynamics, you assume, oh, you have the first law, you have the second law, and then you derive a bunch of stuff. You derive the state equation for gas, for example. Right. So you can things you can work with. The first law and the second law are the postulates, but now the second law is proved. That must mean something more fundamental is assumed that can be shown to have second law of thermodynamics as its consequence. This is again very intriguing. Okay, anyway, so much stuff to learn. So the theorem 2.5.3 says the following. It says, okay, this is a rather ugly looking statement, but anyway, this says d of pxy and q of x and y. So that's the relative entropy between two joint distributions equals d of p of x and q of x. Okay, and then plus d of, here you get the conditional stuff. Okay. P of y given x and q of y given x. Okay, that's the chain rule for the relative entropy. Okay. All right, so once again, compare this with something perhaps more familiar. What's the chain rule? The ordinary chain rule. And so not the ordinary chain rule, but the chain rule for entropy, for the joint entropy is what? Okay, so OneNote is getting very laggy. See? So just to review, for the sake of review, this is reminiscent to the form of h xy equals h of x plus h of y given x. Here, the diagram. H of xy is the big one, so here you have h of y, yeah, h of x. This part is h of y given x. So you can isolate one variable. Okay, here isolate x, and then use x as condition. Use x as condition here. So this is very reminiscent to the chain rule for entropy. Okay, so now let's use the definition to do the proof. Okay. So once again, I think it has some funny business with the log. So there you go. Let's start with this expression. So proof. dp of x and y and q of x and y. So that's the double sum x and y, p of x and y, the log of p of y given x over q of y given x. Okay, and then what else? So we want that. We want p of x and q of x. So perhaps it's a good idea to actually no. This is wrong. This is wrong. This is the joint. This is a conditional version. You don't need the bar in between. Okay, sorry about that. So I think here you just use the joint distribution here. Multiple colors are really beautiful, huge improvement in my opinion. I was thinking about this, the greatest YouTube math channel. This might be. Wow, are you sure about that? Thank you so much. Multiple color, you mean this sort of different color nodes? Why sort of blue is the default color, red is highlights, green is like side nodes, comments, and that sort of stuff. You mean that multiple colors? Yeah, this is how I usually take notes, basically. And because now you wish to cook up a conditional distribution, so it's natural to express the joint distribution in terms of the marginal and the conditional. Yeah, it's nice to look at, I know, right? So you have the log of px times the conditional. Okay, and at the bottom, and then you do some funny business with, not funny, but just the property of log. So I think the whole reason you use log is to have additivity. You want additivity, therefore there's this log in the definition of the entropy. This is so far my instinct is about this definition. Okay, oh, q of y given x. All right, so time to break this thing apart. So you get the double sum over xy, pxy, the log of px over qx. Yeah, use the property of log. You break down that, you get two sums. Right, and p of y given x, and then you get q of y given x. So that's pretty nice. And that's just exactly the definitions, right? So we have what we needed. The first one is the chaotic divergence of px and qx. Remember the double sum over in which the double sum, the first double sum over y vanishes because the sum over y has nothing to do with the last term, so you end up just summing over the joint distribution, which gives you the marginal distribution of x. Oh, an introduction to statistical thermodynamics by Terrell Hill in physics textbook. You know what, guys? I don't know. Like, I hate to branch out too much because I already accused of doing too many subjects in 1 week. I know, like, I should probably focus at some point. This way, yeah, I should probably focus just for my own good. But at some point, I'd like to do some physics on the channel. Okay, just like how applied mathematicians approach physics, say, compared to how physicists approach physics. I think that would be a fun experience to have. But anyway, perhaps thermodynamics is high on the list because a lot of the channel stuff has to do with stochastic, statistics, that sort of stuff. And typically speaking, statisticians, surprisingly, in my experience, okay, in academia or in the industry, don't know much about statistical mechanics. For some reason, this seems to be the most natural field of physics that is closest to statistician point of view, but when I was in university, I struggled to find one department member that is well versed in both. Okay, in physics, I couldn't find a professor who was well versed in statistics, and in stat department, I couldn't find one that is well versed in, say, like high level statistical mechanics, which is kind of interesting. Anyway, so this is the chain rule proof. Once again, it is rather straightforward. Okay, so now let's come to a rather familiar topic, hopefully, is the Jensen's inequality, 2.6. Jensen's inequality. So the inequality part of the information theory is particularly intriguing, in my opinion, because what we just mentioned, the second law is inequality. Right. The second law of thermodynamic, entropy cannot decrease. Right. Of course, that's there's gonna be entropy entropy can be created, right, but cannot decrease. So it's an inequality statement. Here, we're talking about Jensen's inequality. Right? Perhaps the most important inequality related to concavity. And there's so many consequences, and it's used a lot in probability theory. So many corollaries, okay, that follows from it. Sorry, my mouse is getting a little bit weird. Jensen's inequality and its consequences. Yeah, thanks for recommending the thermal book. Okay. And I think a big problem for statisticians to get a hold of say statistical mechanics is its frequent usage of quantum theory, right? So perhaps that's a little bit an extra, like just the style of exposition is a little bit harder for statisticians to swallow. Right? Typically, I think statistical mechanics, based on my limited experience, makes a lot of reference to quantum theory. So that's another big prerequisite, right? So I guess that's perhaps the reason, one of the reasons that not many statisticians bother to look too much deeper into it, which is really a shame. Okay, anyway, let's continue. So here you have the definition of a convex function. Definition. Here you have, let's say f is a function over the interval a to b to r. Right? F is convex if you have the following condition: for every x1, x2 in a to b, and for every lambda in the closed interval 0 to 1, you have the following relation, namely f of lambda x1 plus 1 minus lambda x2 is less than or equal to, yeah, I agree with you, right? So it's the prerequisite thing. Lambda f of x1 plus, but I think that's a little bit digression, because as far as I can recall, Leonard Susskind, you guys probably heard of him. He's a theoretical physicist from Stanford, and he has a whole series on YouTube called Theoretical Minimum. Right? So in the Theoretical Minimum, he remarked that statistical mechanics is not physics, it's a branch of probability theory. So I was fascinated by that remark, so I was trying to locate, okay, a book or a paper that goes along somewhere goes along the line of statistical mechanics for probabilist or statistical mechanics for statistician. I couldn't find anything of the sort. So which is really interesting to me. And in real life, I struggle to find particular individuals that are well versed in both areas. So anyway, so that's the definition of convex function. Of course, it has a nice geometric interpretation. There you go. This is the convex function. So let's say this is the interval a to b. And pick any 2 points, x1, x2. Say x1 is less than x2. The left-hand side is a point somewhere in the middle of x1, x2. If lambda equals 1/2, that's the midpoint, right? So it's just a general point that lies between x1 and x2. And on the right-hand side, is the weighted average. The weighted average. So it basically says the chord always lies above the graph. Okay, so let me highlight that. This is the left-hand side. This part is the left-hand side. And this part is the right-hand side. Okay, I know the text is perhaps a little bit small. I should probably draw a bigger picture. So that's the definition of convexity. Okay, so here you have a convex function. And then you have the follow-up definition. F is concave if minus f is convex. Okay, simple. So a function is convex if it lies below any chord. A function is concave if it lies above any chord. Of course, there are tons of examples. Convex functions includes x squared, absolute value of x, e to the x. Apparently, x times the log of x is a convex function. Better visualize that. X squared equal to 0, apparently. Perhaps we can calculate the second derivative to check. Okay, so just do a quick check. Because that's not a standard function. Okay, x times the log of x. First derivative is log of x plus, well, x times 1 over x is just 1. Okay, and then you have the second derivative. Let's do the second derivative test. You get 1 over x. This is positive. Biostat math. Okay, great. Okay, awesome. Biostat math, undergrad, minor physics, did mathematical physics, ENM. Okay, that's awesome. That's awesome. That's really awesome. I didn't do that much. Okay. So yeah, I'm an applied math graduate, grad student, and I did. Yeah, I did stat major actually. I did stat major and applied math minor as an undergrad, but I pretty much end up actually, even though I have just a minor, I took more applied math than required. So because near the end of my undergrad career, I gravitated more towards applied mathematics than statistics. But still, like and my grad program is in applied math. Okay, I'll say as much as about that. Okay, so that's it. Anyway, the background does not matter. Okay, I don't think background matters that much. What matters is your stamina, really. Okay, anyway, enough digression. So basically, we wanted to graph this function. What does log x times log of x look like? Okay, so when x is positive, as we mentioned, when x is 0, we treat the function as 0. Okay, and when x is 1, is just 0. It's another 0. Okay, and clearly we can see there's a critical point. The critical point is e to the minus 1. So that's actually, sorry, bad drawing. So there you go. So if the function is indeed concave, and I believe, yeah, the slope near origin should be infinite. That's actually a feature. The slope near origin is infinite. So that's log x times log of x. Yeah. So that's awesome, Peter. Did you do quantum too? So yeah, that's the convex function. And you have concave functions as well. So concave function, some well-known example. Concave function would include log. Okay, log itself is concave. Square root of x is concave. Right. So these are nice examples. And of course, you have convex and concave. The only one, right, if a function is both convex and concave, it has to be linear. I didn't prove this, but I think it's true. Of course, if you assume twice differentiability, that's trivial, right? If a function f is twice differentiable and is concave and convex, the second derivative must vanish, so it has to be linear. I don't know if this is generally true. Like if you don't assume any sort of smoothness at all, do you still get linear function? Okay. And of course, ax plus b is linear functions. Straight line functions are convex and concave. But is a converse true? Could be an interesting quiz problem though. I have to work that out myself first. Okay, slight digression. And it says, convexity underlies many of the basic properties of information theoretic quantities, such as entropy and mutual information. Before we prove some of the properties, we derive some simple results for convex functions. So that's why you need things like Jensen's inequality and whatnot. Okay, so yeah. So first you have a theorem from basic calculus, the second derivative test, the well-known and loved second derivative test. Okay, so now if f double prime, let's say if f double prime is non-negative, greater or equal to 0, okay, or less than or equal to 0, non-negative, or actually strictly greater than 0, over an interval. Over an interval, then the function is convex or strictly convex over that interval. So strictly convex means the inequality only holds when lambda equals 0 or lambda equals 1. Okay, so here strict convexity means equality holds if and only if lambda equals 0 or 1. All right, so next theorem, this theorem is basically the second derivative test in calculus. And you prove it using the Taylor expansion as usual. Over an interval, then the function is convex. Over that interval. Do we need to go through that proof? Or should we just hand wave? Okay, let's see the proof. Okay, let's see the proof. So we can use the Taylor expansion. So here, let's assume x naught is a point in that interval, in the interior of that interval.
be an interior point, because whenever you do differentiation, you want interior points. Okay, let x and x naught be interior points. Differentiation hates boundary points. So that's why in manifold theory, you always use open sets. Let x and x naught be interior points. Of the interval. And then you use Taylor expansion. So f of x equals f of x naught plus f prime of x naught times x minus x naught. It's just a good old second derivative test, okay? And then you use the Lagrange form, or what's it called? I think it's called the Lagrange form, right? The Lagrange form of the Taylor theorem. You get a remainder, which is a second derivative evaluated at some point between x naught and x over 2x minus x naught squared. That's a Lagrange form, where x star is between x naught and x. So by the hypothesis, while the last term is positive, non-negative, right? So by the hypothesis, greater or equal to 0 by hypothesis. Okay, and now you can take your x naught to be the midpoint here. So you write x naught equals 1 minus lambda of x1. Once again, we assume x1, x2 are interior points as well, okay, which are also interior points. Lambda times x1 plus, okay, the software is lagging, okay, 1 minus lambda x2. Oh no, looks terrible. Okay, so my mouse is doing some funny business. Okay, so looks a bit weird. All right, so what do we have? So this is our x naught. This is our x naught, and then let's call this star. All right. So in star, let's take x to be x1. And start at x be x1. This way you have f of x1 is greater or equal to f of x naught plus f prime of x naught times x minus x naught. What is x minus x naught though? X minus x naught, just do the calculation. You get 1 minus lambda times x1 minus x2. There you go. Okay, and well, you probably see what's coming. And then in x star, you let x equals x2. Then f of x2 is greater or equal to f of x naught plus f prime of x naught. And now you have x2 minus x naught. But x2 minus x naught is what? Is lambda times x1 minus x naught. x1 minus x2. Okay? That's cool. So let's call this equation 1 and let's call this equation 2. So you multiply equation 1 by 1 minus lambda, I believe. actually by lambda, you want to cook up a lambda times f of x1, right? So 1 times lambda plus 2 times 1 minus lambda gives you the following. So lambda times f of x1 plus 1 minus lambda times f of x2 equals what? Equals, well, just f of x naught. Because you get lambda times f of x naught plus 1 minus lambda times f of x naught. F of x naught times lambda cancels, so you just get f of x naught. And the product on the right-hand side cancels because here you get multiplied by a lambda factor, here you get multiplied by a minus lambda factor. They actually here, I think I made a mistake here. In here it should be x2 minus x1 so that you can have cancellation. Yeah, x2 minus x1. That will do. Oh, not equal, actually. It should be greater or equal to. And that's exactly what we wanted. So yeah, it's just a classic proof using Taylor expansion. Oh no, you see, it's not responding. Yeah, okay, so it's lagging. I think is there something I can do about it? Go to the option. Is there like AI features that auto check or something can be turned off, huh? Is that advanced probably? Is this sort of thing can be I don't know. Like I don't know which one. I think there's something you can turn off so it becomes less laggy. Because right, sometimes OneNote hates when you draw too much. Ah, okay. So writing is okay, huh? Okay, I'll take a look at it later. This is getting annoying. All right. So that's the second derivative test. Okay. So now we have the Jensen's inequality. Perhaps that's the most important inequality in information theory, it is said. Okay. So here you go. You get the theorem that says this is Jensen's. I just opened a new page when it started lag too much. Okay, fair enough. Okay. It says if f is convex, I'll see how long I can suffer through this. Okay. Okay. Anyway, I try to keep all the nodes in one file for one stream. This way it's easier to do reference and whatnot. Okay, so here you have if f is a convex function, then e of f of x is greater or equal to f of e of x. It's the same idea as the chord story. Right? Because you see on the right hand side, this is an average, basically expected value. And on the left, you have f of an average, so f of an expected value. So f of a expected value is less than or equal to the expected value of f of x. There are tons of non-trivial inequalities that follows from this. Things like Cauchy-Schwarz, Holder can be proved from this. All right. So the proof is uses induction argument. Actually here in the main text, it is proved using the induction for discrete distribution. But I don't think that's necessary. So you can, I think you can come up with an argument that, okay, if a function is convex, then it's always above the tangent. If a function is convex, I think you can. The classic proof for Jensen's equalities says if f is use the fact that if f is convex, then you can say, okay, if f is convex, it doesn't have to be actually differentiable. But basically, if f is convex, then at any point you can find a line. Here I'm using the tangent line as for illustration purpose, but it doesn't have to be literally a tangent line. At any point it is above a line. Is it an economics branch? What do you mean? Well, information theory is used in economics, though. This is the information theory session. So I think I'm going to claim without proof that f is convex implies for every x, okay, in the domain of f, of course, f of x is greater or equal to, actually, for every x naught, this is the base point. Okay, f of x is greater or equal to some line. Let's just call it m. The slope is m. The slope is m times x minus x naught plus f of x naught. And this is true for every x, for some m. Basically, is for every point, for every base point x naught, there exists m. Okay, there exists m. So the order of quantifier matters. Yeah, I think it's called a supporting line, right? It's called a supporting line. That's an excellent remark. Indeed, it's a supporting line. There's a proof in Hardy's inequality. I'm not sure which inequality that is. I'm not super well versed when it comes to inequalities. I only know the well-known ones. Yeah, thank you very much. I'm not sure how to pronounce your name, but I'll credit you for it. Okay. So this is a great remark. So this is called a supporting line. So I'm saying is, if f is convex, then it's a book. Oh, Hardy's inequality, that's a book. Okay, great. So, yeah, Hardy has written some good books. His Pure Math, his book, I think he wrote a book literally called Pure Math, right? I think it's on analysis, which is pretty, I read a portion of it, quite like it. So there exists m such that for every x this is true. So if we just use that, then the inequality becomes very easy to prove. If you can show this is there is a supporting line, then it becomes really easy to prove. So yeah, this way you just use use this inequality, then expected value of f of x is greater or equal to expected value of this supporting line, which is m big X minus x naught plus f of x plus f of x naught, I believe. Is that how you do it? Oh, actually, you'd have to pick x naught to be mu. Yeah, I remember. We pick x naught to be e of x. That's the trick. So if you pick to be e of x, the first term cancels, and then it just follows. Because f of e of x is already a constant, then it's just f of e of x. We're just gonna leave this inequality as such. Okay. So if you guys are interested in other proofs of Jensen's inequality, I'm pretty sure you can easily look them up. Right. This is such a well-known inequality. All right. So let's finally talk about perhaps a non-trivial inequality. I mean, so far we've only seen equalities, right? And the equalities aren't particularly deep, right? They're nice, but there doesn't seem to be something super surprising going on. Because I figured the chain rule, I think I have this feeling, okay, that these chain rules, which are all equalities, which has this nice visualization and whatnot, these are all artifacts of the log function. I think these are all artifacts of the log function. They convert the laws of probability, which are usually multiplicative, into additive ones. So they look nice. And there's some interpretation to it, right? But I'm still not terribly impressed, okay? But anyway, here we have, I think, a truly non-trivial result. Theorem 2.23, okay? I will spend the last 10 minutes looking at the sufficient statistic part, okay? But I'm not sure if we can actually understand that, okay? So anyway, so this is the information inequality. Information inequality that says the following. If you have px given, okay, given px qx and big X in scripted x, okay, these are PMFs. Then you have what? Then you have the KL divergence is non-negative. Information inequality. So one of the reasons it works like a distance. And equality if and only if P and Q are the same. So that's the information inequality. Let's box that. All right. So do you need to use the convexity of the log? Probably. Yeah, because this is a expectation of a log something. So let's try to do that. So d hold on. Log is convex. Log is concave. So let's use minus log. Right? Minus log is convex. So here p of d, p, and q. Okay, that's the expectation. That's the expectation using p as the probability measure of minus. Oh, there's no minus. Just actually this. Yeah, by definition, this is p of x times. P of x times. No. You don't need p of x. You need the log likelihood. What am I doing? The log likelihood of p of x over q of x. That's nice. But as I was saying, Log is concave, so put a minus sign. Put a minus sign. All right. So now minus log is convex. So you can use the Jensen's inequality. This is greater or equal to minus log of expectation P of x over Q of x. All right. Doesn't seem very nice because I can't say much about it. You know what, guys? I'm going to change. I'm going to write it as follows. So it's okay if we have a concave function. We just reverse the sign in the reverse the inequality sign in the convex in the Jensen's inequality, right? So let's do, because I really want P to be downstairs. You want an EQ instead? Well, the definition is EP. Right? The definition of relative entropy says if you treat P as a true distribution and then calculate the expectation. Yeah, there's nothing wrong with that, right? So remember, this is just the sum of, okay, minus, put here, the sum over x, P of x log of px over qx. Right, so this is what we wanted, and I'm going to swap that to EP log of q over p. Okay. But log is what? Log is concave. Log is concave. So look at the picture. So this is log. The average of log is less than, no? Yeah, the average of log is less than. This is log. I'm saying is the average of log is less than the log of average. So this is much nicer, right? This is much nicer because what's that? EP of qx over px is just the sum of px times qx over px. It's just the sum of qx, which is 1. Px cancels, is just the sum of qx, which is just 1 by normalization. So this is just 1, so that's just the log of 0. Oh, sorry, log of 1, which is 0. And therefore, boom, as needed. Okay, here we use Jensen. All right, so that's done. That's the information inequality. So that's pretty non-trivial, in my opinion. Pretty much everything that follows Jensen feels non-trivial to me. I don't know about you guys. All right, so I think we're gonna stop for now, and instead we're going to go to the MIT OpenCourseware. There's this hold on, particular set of notes on sufficient statistics here. Is there sufficiency? No, it doesn't cover sufficiency. Huh? Data processing theorem, maximum entropy. Yeah, this is what. Oh, yeah, that's the second law here. There's a second law. Okay. Anyway, let's come back to the. Actually, I don't think we have time to deal with sufficiency. That's unfortunate. But anyway, let's try to do a problem, shall we? Let's do a problem to wrap up the stream because it's kind of getting late. Let's do a problem. Okay. So yeah, that follows from the strict concavity. Well, it's actually, yeah, concavity, exactly, you're right. I don't know which exercise are appropriate right now, but I mean, perhaps 2.1 is doable. Okay, I'm just going to uh, paste that here. Okay, to wrap up the stream, let's do a little problem. So this is problem 2.1 because I didn't have time in advance to look at, well, I didn't even have time in advance to look at the theory. So, and typically when you have very little clue of which exercise is more important, well, we just follow the order of the text. So you have a fair coin is flipped until the first head occurs. So that's a geometric distribution. Be the number of flips required, so x just is geometric distribution. Solution: x follows GOP. So probability function of x, right? So here is the number of flips required, so x takes values in 1, 2, 3, and so on. So probability of x is p. Probability of big X equals little x is p times 1 minus p x minus 1. So when x equals 1, you just need 1. That means only one toss gives you success, which of course has probability of p. And so to have little x minus 1 flips means x minus 1 failures. So x 1 minus p to the x minus 1. That's the probability function. So entropy is just application of that. Okay, so entropy is negative sum p of x log p of x. So it's just a series summation problem. Right. So here you have even given the nice identities to work with. So that's minus x from 1 to infinity, p 1 minus p to the x minus 1. Taking the log, that gives you, well, you get two terms, which is log of p plus x minus 1, log of 1 minus p. Right? There you go. And so you get two series, minus p log p, sum of x from 1 to infinity, 1 minus p x minus 1, plus p log 1 minus p, the sum of so So now you have, the first one is a geometric series. The second is a geometric series with a linear factor at the front. All right. And by a swap of index, this is just the sum of 1 minus p, sum of 1 minus p to the n from 0 to infinity. So this is 1 minus p log of p times 1 over 1 minus p, geometric series. And the second one is p log of 1 minus p times, well, just the second series, so that's r equals 1 minus p, is 1 minus p over 1 minus 1 minus p, so that's just p squared. Okay, so p cancels, this way you get minus log p. So here you get log of 1 minus p times 1 minus p over p. Doesn't look like you can simplify this further. Okay, so that's part A, I guess. That's part A, I guess. I mean, you can, I think you can look up in the Wikipedia for geometric distribution. And there's usually a bunch of formulas, including mean variance, the moment generating function, and whatnot. Okay, here's the entropy. Yeah, it's the same as we just derived. Okay. Anyway, so that's entropy. And B, okay, B says a random variable x is drawn according to this distribution. Sure. Find an efficient sequence of yes/no question of the form: is x contained in the set S? Compare h of x to the expected number of questions required to determine x. Is x contained in the set S? Find a quote-unquote efficient. You see, this is very vague, right? Because we did one example earlier about this sort of questioning. We start from asking whether x equals the value that takes the highest probability. Right? So that seems to be the intuition here. The geometric distribution decays in monotone. It decays in a monotone manner. So the first one, the first value is just, when x equals 1 is just p. You can visualize the distribution as such. When x equals 1, that's p. And then the probability just decreases in a geometric way. So is S contained in the set S? So why don't we consider the CDF, huh? Why don't we consider CDF? So the probability of big X greater or equal to little x, the tail probability, that's the complementary CDF, is 1 minus p to the x. Indeed, when x equals 1, when little x equals 1, so probability of big X greater or equal to 1, that means you takes at least one trial, actually it should be 1 minus 1. Okay, sorry, it should be minus 1. Yeah. If it's greater or equal to 2, that means the first one is a failure. That means the first one is a failure, so, or should we ask if x is odd or even, if we want to balance the probability of yes and no? I'm not quite sure, right? I'm not quite sure. So, I mean, this is this is vague. This is because we don't have a criteria for so-called efficiency, right? So I was just thinking about this example we did earlier. Right? Here, x can take four values, a, b, c, d. And the values a, b, c, d has probability in a descending manner. So here it says in the text, it says an efficient first question is x equals a. Start from the highest, start from the outcome with the highest probability. Right. I guess you can ask, is x equals 1? Is x equals 2? That would be the idea here. Perhaps we can use inequality. As I was thinking about inequalities here, let's say is x has to be greater or equal to 1. That's beyond question. Right? So that's for sure. That's 100% true. So we can say is x greater or equal to 2? If x is greater or equal to 2, if you get yes, well, you keep asking. If no, then it has to be 1. So this is my idea. Isn't it the smallest amount of question on average? Right. Theoretically speaking, you should have some sort of minimization procedure, right? It's the smallest, quote unquote, efficient. Quote unquote efficient. So yeah, in a sense that is optimal. In a sense that is optimal. So I'm having a hard time trying to formulate the optimization problem though. So let's say the idea is given a sequence of question, like let's say given a sequence of question, you run the sequence until you can determine the value of x. It's like some sort of waiting time, random variable. And then you calculate the expected value of that waiting time random variable, which will be a functional of the questioning sequence, which will be a function of the questioning sequence. And then you minimize the functional over that functional sequence. I don't know how to formulate the optimal procedure. It just feels to me that it is intuitive that you ask, okay, I know, I mean, this intuitive is not proved. Okay, so you ask, is x greater or equal to 2? Is x greater or equal to 3? And so on. It just proceeds that way. Seems like we're looking for a binary split closest to 50-50. Like a binary search. Oh, actually, here, I think it's assumed that h is the coin is fair. Yeah, it's fair. Exactly like that. It's 50-50. So sorry guys, I forgot to assume p is 1/2. So p is 1/2. So h of x is actually minus. Let me just evaluate that real quick. Okay, so this log 2 plus log 1/2 times 2. No, times 1. Hold on a second, is that 0? It shouldn't be 0. Did I messed up again? Yeah, I messed up. This should be a minus sign. My goodness, I was sloppy today. It should be a minus. This way you get 2. Sorry, not 2, but 1.
Is that 2 or 1? Is log of 2. Yeah, it should be 2. Yeah, you missed the minus sign here. Exactly. I just changed it. Thank you so much. Because, yeah, I was plugging the value and figured something is not right. So, yeah, P is 1/2. So this simplifies to log 2 plus log 2. So it's 2 log 2. And when you use base 2, you just get 2. Right? So, and now this is just half. Is exactly what's you guys are saying. It's like binary search. So x equals 1, 2, and so on. So ask if is x greater or equal to 2. Yeah. Um, thank you so much. Thank you so much for joining the stream. So is x greater or equal to 2? If you're not on Discord, I strongly recommend you join the Discord. We have a lot of discussion there. So is x equal to 2? Is x greater or equal to 3? Right? Yes with probability 1/2, no with probability 1/2. Right? And now is x greater to 3? Well, that's 1/4. No is 1/4. That's the questioning sequence. So given this questioning sequence, given this, what's the length of the given this sequence, let n be the number of questions needed, which is also a geometric distribution. Then expected number of questions required. And this is the number of questions needed. All right. So think about this. So if x can take value 1, 2, 3, and so on, and the corresponding n would be what? If x equals 1, then you just need one question. And x equals 2, you need two questions. Right. So think about it. So if x equals 1, when you ask the first question, the answer is no, then you get the answer. If x equals 2, well, the first question will be yes, but you need to keep going. The second question fails, so you get that. So it's clear that x always equals n. So therefore, the expected value of n is just expected value of x, but for geometric distribution, that's well known, which is just 2. So it happens to be just hx, which is nice. Right? The entropy is the expected number of questions. All right, so thank you guys very much for watching the stream, and I think it's a good time to stop. Okay. Perhaps I'll take a look at the sufficient statistic on my own, and perhaps we might even pull out the information theory text in the mathematical statistics stream. Like, who knows? But this is certainly a very eye-opening experience, and I enjoy this a lot. Unfortunately, I cannot promise I will come back to this material in near future. We'll see how things go. Okay. So anyway, guys, thank you very much for watching.